Good morning, everyone, to this very cozy morning session. It is titled Multimodal Learning, Data Fusion, and Image Processing. And my name is Attila. I'm from Umeå University in Sweden.
My name is Daniel Moyer. I'm from the Vanderbilt University in the United States.
And I think we get started with the first presentation titled Disk Clip, Arbitrary Metadata and Image-Guided MRI Harmonization via Disentangled Dynamic Contrast Representations by Mehmet Avci. So let's welcome him on stage.
Hi, good morning, everyone. Thank you very much for being here in this lovely weather. My name is Mehmet Avci. I'll present our work, Disk Clip, Unified Harmonization Disentanglement work. So, as you already know, one of the major problems in radiology AI is domain shift, which is caused by huge acquisition variability due to different hardware vendors, different scanners, different acquisition protocols that produce visually very different images of the same anatomy, which creates these large domain shifts. So domain shift basically means when you train a model on scanner A, the performance doesn't usually translate to the images from scanner B, not because of biology or the underlying population has changed, but rather the contrast has changed. And this limits the clinical generalization and safety. And one solution is harmonization, but current methods have several limitations. Image-based methods usually require a reference image, which might not be always available. And text-guided methods rely on coarse tables like T1 or T2, but doesn't exactly say what kind of T1, what kind of T2, because there are many other parameters. And they don't really capture the real-world acquisition complexity. So what would be an ideal harmonization framework would look like? So it should be given an MRI scan with any kind of acquisition setting. It should be able to synthesize a target protocol through either a reference image or target metadata while preserving all the anatomical content. So it should be not just cross-modality, it should be also do cross scanner as well. So it should be able to synthesize all kind of contrasts. And for this, it needs to have some understanding of the physics. It needs to understand this parameter space. So it should be acquisition aware. And to be able to do this without paired data during inference time. And we try to take a step towards this ideal framework and propose a two-stage approach. And the first step is the understanding the image contrast, where we align images with the metadata to achieve this. And for this, in our previous work, we proposed MR clip, where we aligned MR images with their DICOM metadata. And for metadata, we use information of scanner, sequence, and numerical parameters like echo time, repetition time, inversion time, and flip angle. And the resulting representations will hold the contrast information. And now we have the contrast information, now we understand contrast. On top of these, if we can disentangle the anatomy, we can basically use these representations and give it to a decoder architecture to harmonize and get the final images. And you can see the overall framework here. So, as you can see in the top left corner, the first thing is we basically map a source image into an anatomical representation. And we get the contrast from the pre-trained MR clip encoders, either through an image or a metadata, and we feed this to this style fusion decoder to get the final harmonized image. To achieve this, we propose this new architecture called style fusion decoder, which is basically a UNet, but it has these adaptive style transfer blocks in its bottleneck and decoder layers. It has attention and ADA in adaptive instance normalization blocks to modulate the features. And you can see our loss functions here. So the important thing here is how do we get anatomical representations. We achieve this by using this patch-wise contrastive loss, which basically aligns patches on the same location, which is seen by green patches, and pushes the patches that are on the different location, which are correspond to red ones. And to achieve high fidelity harmonization, we use reconstruction loss, we use MSE loss, perception loss, adversary loss, and we support the style alignment with clip-based losses. Our dataset is real-world clinical data. And for the first stage, we have 40,000 subjects with 107,000 scans. And second stage, for the harmonization training, we have 20,000 paired scans. And we have 20,000 unique DICOM metadata combinations. And you can see the heterogeneity of the acquisition protocols here. So on the left, you can see the type of scanners we have. On the middle, we have many different sequence types, and you can see the huge heterogeneity of the numerical distribution on the right. Looking at the results, you can see an example of anatomical representations. So what you see here is we have a single patient, but has 4 different sequences, and their corresponding anatomical representations. So anatomical representations are here. It acts like a pseudo-contrast. They look more similar. And the important thing here is we don't want the anatomical representations of different sequences to be exactly the same. Rather, we want the acquisition-induced intensity differences to be suppressed so that we can have a base and then the decoder can inject the style better and easier. And this works quite well. You can see the harmonization results. On the rightmost column is image-guided, and next to it is text-guided or metadata-guided. And compared to baselines, visual results show that our methods can preserve the anatomy better and produce high-fidelity outputs compared to baselines. And also on row 3, where there is a pathology, you can also see that our model can preserve the pathological region better than the baselines. You can see the numerical results here, PSNR and SSIM. Columns represent the source modalities, rows represent the target modalities. And overall, when you look at the heat maps, you can see we have more greens compared to baselines, which means that we can significantly outperform the baselines. This is on our own data, and if you test it on unseen data on zero-shot setting for our own model, but the baselines were trained on this data set, we see that on flare to T2 and T2 to flare translation, image-guided method comparably performs compared to baselines, where the metadata-guided suffers from a bigger loss because the acquisition protocols are unseen, especially the scanner, and even the magnetic field strength is different here, but it has to rely on the numerical parameters only. We do an ablation of the components, and we observe the biggest performance gain is coming from the proposed AST blocks, and it improves the performance up to 7 point of PSNR, and the other components also gradually adds up, and the overall framework gives the best overall result. Our work has several limitations. First, it depends on the quality and the completeness of the DICOM metadata, which may have some problems because it's a clinical data. We currently operate on 2D slices. It doesn't explicitly enforce true plane consistency. We haven't shown any downstream impact yet, and we focus on brain MRIs. It's not modality or organ specific, but extension to other modalities and organs needs more validation. To conclude, we introduced this clip, a unified MRI harmonization framework that can operate on either images and the metadata. And to achieve this, we propose a new style transfer architecture that enables a more robust generalization across scanners, sites, and protocols. We significantly outperform baselines in both style translation and anatomical preservation. And together, we think these contributions lay the groundwork for acquisition-aware medical imaging. I think we need to make the models more understand the underlying acquisition so that they will be more robust and interpretable and safe across clinical environments, will be more safe against these changes. Thank you very much. Our code and weights are publicly available. And let me know if you have any questions. Thank you.
Thank you very much. We have 2 microphones up in the front. If you have any questions, feel free to come up. But I think it's really exciting work. I have a lot of questions, but I'll stick to just a few of them. DICOM metadata can be really messy when it comes to different scanners. So I'm wondering, do you have to extract the required numbers manually, or can it handle the DICOM metadata directly?
Yeah, good question. Yeah, there are many DICOM parameters, hundreds of them. We try to choose the most informative ones, like 10 of them. We don't do any processing except maybe scaling the numerical parameters from seconds to milliseconds, like do the conversion. Other than that, we don't do any other processing. It's raw data.
Oh, we have a question.
So yeah, maybe thank you for the great presentation. Maybe a similar question. Did you consider running an LLM on the DICOM header to extract information more structurally?
Yeah, that's also a good suggestion. We actually did. On the MR clip training, we used Biomed clip, which is a pre-trained big clip model. Because this is very specialized task, Biomed clip failed, and we tried to fine-tune it because Biomed clip has a pre-trained. It's not an LLM, but it has a big language model, transformer model, but it also failed. So yeah.
And just out of curiosity, you mentioned that one of the limitations is the completeness of the metadata. What happens if you have one missing?
Oh yeah, I forgot to mention, having set the limitations, we have an extension coming up, hopefully to appear on arXiv next week if you're interested. And yeah, we have several suggestions for that problem. We use cosine similarities because we trained the clip with cosine similarities. And if the cosine similarity of a normal image with a problematic metadata, because it should drop because we normally align. And hopefully, because we have a large number of data, hopefully bad cases will be added like as a noise rather than disrupting the model. Yeah.
Thank you very much. Let's thank the speaker again.
Thank you very much.
All right, so we'll move to our second speaker, who is Nusrat Nizam, speaking about XCardia, phenotype-guided cross-modal alignment for opportunistic cardiac screening of routine chest CT. I believe we have Sunwoo Kwok instead.
Hi everyone. Today I'm going to present the XCardia, the phenotype-guided cross-modal alignment for opportunistic cardiac screening on routine chest CT. Yeah, like you know, I'm a Sunwoo Kwok. I'm on behalf of the Nusrat, the first author of this paper. She couldn't make it, unfortunately, but I'll try my best to deliver this work. Here's an outline. And let's start with the background and the motivation. So cardiac care is inherently a multimodal. So in clinical setting, oftentimes clinicians will go check many different type of modality. They check images, labs, echocardiogram, ECG, and many more. And all those multimodal setup will help them have a better holistic patient view, reduce the uncertainty, and oftentimes it can help them detect the rare disease, which probably couldn't possible with the single modality diagnosis. And obviously, we want this happen with our AI model too. And that's why we believe multimodal AI is a future. However, there's big challenges in this multimodal AI learning. And then the core challenges with this multimodal AI is how do we combine all this heterogeneous data information put it into the single feature space. And that's why we need a really effective cross-modal alignment. So if there's modality A and there's modality B, there are probably some area they overlap and share some information. And there are also some information they don't share at all. And however, we want both homogeneity and the heterogeneity information to be online in a single space, so we can close the gap, close the modality gap, and also we fully leverage all the rich information from all the modality we are using. Also, another alignment we really care about in this specific case is actually cardiac to non-cardiac modality alignment. So question we pose here is how can we leverage the structural tabular cardiac data to enhance the analysis of non-cardiac medical images? So here we have a non-contrast chest CT, which often used in routine checkup for the various reasons. Usually it's for very general purposes. It can be used for many different reasons. However, we want to see, can we actually predict any of the cardiac abnormalities from this routine checkup? Because if that's possible, it actually opens a window for the opportunistic screening for the better cardiac care by flagging the clinician from routine checkup. And let's talk about the data first. So for our data, on our pre-training cohort, we use around 20,000 patients. And each patient has 3 different modalities: echocardiogram, ECG, and the 3D CT chest scans. And we put echocardiogram and ECG information into the tabular data. And then also we have image modality from the CT volumes. And it's important to note that all of them are obtained within 6 months from each other. So we try to minimize the time gap between each modality. Additionally, we also perform the supervised downstream task using with around 7,500 patients with the 16,000 chest CT studies. And you can see here that on our test set, we have 10 different labels. And I want to note that all of them are actually binarized for the normal and abnormal. Before we go to our method, let's talk about the related works first. So first one will be the MMCL, the multimodal contrastive learning, a very straightforward one. We have 2 different modality, go through the independent encoder, and then we perform clip-style training with the contrast loss. Another one is a SimClear, is actually the single modality unsupervised method, and they push and pull between different images with augmentation. Actually, the key part of this related work will be the non-parametric Nerdaria-Watson head. So this is about, for the given query sample, we actually pull and construct the support set from positive label, and then we sort of do the average weighting prediction based on the distance from query and the support sets. And let's talk about the methodology. So our method is basically the combination between NW head and the MMCL. So here, first, we do the very classic setup for the MMCL. We run through the non-cardiac CT with the image encoder, and then we run through our tabular data with the tabular encoder. And then we perform the clip-style training for the cross-modal alignment. And another part of our training is the non-parametric phenotype prediction. For this one, for the given query, we actually fuse the embedding from the CT and also tabular data. And then for that given query embedding, we pull some of the support set per label. And then we do the average weighted prediction based on the distance from query and the support set. And then obviously we combine those two components into one. So we have a clip loss combined with the NW loss with the scaling lambda. And for the fine-tuning stage, we only use the 3D CT volume with the frozen image encoder and the trainable task head to predict the final binarized cardiac anomaly predictions. And let's check the result here. So for the result, you can, on the left is a full fine-tuned result. And those no pre-training is actually the straightforward supervised result. And you can see that comparing to all the baseline we have, our proposed model actually performed best on most of the labels. More importantly, on the right side, you can see that when we perform the 5-shot learning, our model actually could superior over all the baseline by the big margins, which suggests that our model is very sample efficient in training. Here's a PCA visualization of multimodal embeddings. And we try to see whether the image features and the tabular features are actually aligned in a single space. And you can see that for the SimClear and the MLCL, you can easily distinguish those two, separate them in the PCA visualization. However, for our proposed model, you can see that all those features are actually very well mingled into one space, which suggests that model alignment happened very well. Actually, let's skip this one. Okay, and interpretability. So we wanted to see that the image encoder actually pay attention to the anatomy of the heart. And you can clearly see that for all those cases, image encoder pay attention to the heart area generally. And also you can see that it actually pay attention to the different part of the heart for the different labels, which suggests that they actually understand the anatomy of the heart. Here's another ablation study. So we try to compare the non-parametric versus learnable head. Like I mentioned before, our phenotype prediction head is actually non-parametric, so there's no learnable parameters there. However, if we make it learnable, they actually, image encoders start to get distracted by it, which means they cannot really pay attention to the heart anatomy, and they almost like start to cheating, and just simply get signal from the clean cardiac-related signal from the tabular data, and just discard all the image information. Also, another ablation study we performed is effect of the training size. We performed 2%, 4%, 6%, and 10%. And across all the training size, even though they're relatively small, our proposed model actually performed very well comparing to the baseline. And it also suggests a strong sample efficiency of our model. Let's skip that. Let's talk about limitations. There's several limitations we have. The big one might be the temporal misalignment. We try to keep it minimum to the 6 months. However, it can be, many things can happen in 6 months, so that's our limitation. Also, we kind of simplify the problem with the binary labels. And there's several more limitations. And I want to finish by thanking our lab members in our group, and also thank the NYP Cornell Cardiovascular AI Collaboration to fund this project. Thank you.
So again, we have 2 microphones at the front if anyone would like to ask questions. But I can start us off. Thank you for a wonderful presentation. I'm very interested. These are extremely disparate modalities, and the encoders for both of them, you are training full training and then fine tuning. Do you feel that for these zero-shot or novel tasks, like the ones in your paper, or the one in your paper, we have a risk of losing information from full training, that by manipulating the image encoder to match a sparse text label, for example, we might also accidentally ablate some of that information?
So, you mean?
yes, here in the upper left, we're training both encoders.
Right.
And the tabular information is very different than the image information.
Right. Right.
So if our downstream task on the far right-hand side is not contained in the tabular information,
Right.
do we risk losing that information from the image?
It can be. I mean, yes, but the idea is that we're trying to set this up as like opportunistic screening setup. So in most cases, so like you said, non-cardiac CT will not be used in the actual cardiac focused treatment. Echo and ECG will give you much better result if you actually can achieve that. But the idea is, can we detect at least some part, or can we flag some of the abnormality from the routine checkup of the chest CT when the clinician didn't really expect anything? So, of course, yeah, if it's provided, it probably give a much better result. However, we set up our problem as like an opportunity screening.
Okay. And I suppose a second question, maybe a little bit more technical. A few slides ahead, we have these PCA plots. And your method has a very spherical plot on the far right-hand side. Is there reasoning behind that? The other two plots are quite collected.
Actually, I'm not sure why that happened. Probably due to some of the dimension reduction of PCA, but yeah.
Thought it was an interesting pattern. Well, seeing no questions, let's thank the speaker again.
Thank you.
And the next presentation is titled Semi-Synthetic Localization Datasets for Radiological Findings on Chest X-rays. And let's welcome Andrea Posada on stage.
Thank you to the area chair for the introduction. And before we start, just in a nutshell, what we do is we generate chest X-rays with precise bounding boxes, so we don't need radiologist annotations. Okay. So for chest X-rays, actually it's a quite common modality. And the classification data sets, we are in a really nice spot. So at the moment, we have hundreds of thousands of X-rays provided. Checks expert. Yeah, okay, sorry. But when we go into the localization data sets, actually, the scenario is a little bit different. So up to April of this year, only 8 publicly available data sets with bounding boxes for more than one radiological finding was available. And in this case, the top largest ones are CXR LA14 and Bindia CXR, with only more than 10,000 X-rays. And why is that? Actually, it's because expert annotation is really expensive. Moreover, we also have that even in the largest of the data set, actually atelectasis was present in only 0.2% of the images. And of course, for us, it will come to mind, let's use synthetic data. The problem here is that if we go fully synthetic, we cannot guarantee, or we don't really know the exact position of the finding. So our research question is, can diffusion-based unsupervised editing augment chest X-rays datasets to add precise localization labels for radiological findings? And the answer is yes. We can do it with semi-syn CXR, and we actually also provide the bounding boxes. And you will be wondering, okay, how does this work? So, okay, I don't have a pointer, but we start on the right side of yours. So we will have as input a healthy chest X-ray and a radiological finding. And in this case, we can see, for example, cardiomegaly, but we have support for the 7 findings that are on the bottom. And we will get as output the edit chest X-ray with a precise matching bounding box. And let's go to the first component, which is the prompt sampler. So for these, and actually here is where we generate the text, which will condition the diffusion process, and we will start extracting the findings impression and last section from the MIMIC CXR reports We also take the phrases that are present in MXCXR, and having these two sources, what we do is we keep single finding phrases, and then we actually simplify also these using an open language model and remove any kind of reference to size and severity. And you will be wondering, okay, and how do we then define the size and severity? But these will be intrinsically defined by the size of the masks. And once we have then these two sources homogenized or like clean, then we will guarantee that actually they are equally likely to be sampled. And we end up with a really nice pool of text prompts, which, like each of them, is accompanied by a frequency to be sampled from. And here on your left side, we could see actually the ones for pleural effusion. And the most likely prompt in this case is bilateral pleural effusions, and as you can see, this already is giving us a hint of where the finding should be located. And this leads us to our next component, which is the mask generator. And for us, this is the most critical component, because it's actually giving us the bounding box that we will use later for object detection. And we need then to guarantee that actually they are anatomically possible. So first, what we do is we feed bounding box size with 1E and 2 MXD. Sorry. Okay, yes, thank you. So here then we are guaranteeing that actually the distributions that we get are reflecting reality. Then we go with anatomical references, so we will leverage the segmentations that are on the long, like the long and hard segmentations that are present on checks marks. And actually, as then we will go in everything relative coordinates, we don't need registration, and that's a really nice property of the framework. Then we will guarantee alignment between the prompt and the masks, and how do we do this? We do it via distribution truncation, and last step is an optional Gaussian blur. And we want to see here is what is the impact at the end of the day in reducing the inpainting anti-refracts and boundary seams. And as you can see, we will have like a logic that is finding related in this case. So lung-related findings will be constrained inside of the lungs, pleural effusions will be anchored to the bases of the lungs, and cardiomegaly will be constrained to the heart, and in this case, we will model it through the cardiothoracic ratio. And last component is how we do the editing. So in this case, we will leverage two existing pre-trained models, that is Roentgen and RAT edit. And we will go with diffusion blending to do the inpainting or the editing of the checked X-rays. So we tried 3 different strategies in this case. The first one is blending after the denoisiness step. We also try with blending before the denoisiness step. And finally, we constrain the classifier-free guidance to the mask. And okay, how do we evaluate this? So first, we need to guarantee the quality. So we use IUROC for detectability that actually the inpainting is successfully inpainted on the X-ray. We also use average precision, not to only see the radiological finding there, but actually that is also well located. FID for visual realism, clip score for text visual alignment, and a reader study also checking realism and detectability. We use 3 experts and 140 checks X-rays. And finally, and this is what matters for us the most, is task performance, because at the end of the day, we are, or our aim was to augment localization datasets, so if we don't get good downstream performance, it doesn't make sense. And we will just use mean average precision for this. So when we go into quality, it's important to remark that at the moment, there are not really baselines for us to compare against. So most of the methods are fully synthetic. So here we just mention them for a reference. And what we aim at the end of the day is to be on par with them, which we actually could see. 2 really particular radiological findings are cardiomegaly and pleural effusion. And we think this is because they are highly localized in the way we are generating the masks. Here are some qualitative examples, and we also have a CLIP score of 30% and FID of 64 that is on par with the baselines. And on the reader study, we could see that actually, although we are a little bit far away still from real checks X-rays in terms of reality, which also could be because we are really constraining the generation process, the finding was recognized 54% of the cases. And what matters for us is does it really help us augmenting with our images? And the answer is yes, and we can effectively address the scarcity and engage the generalization capability. We try, in this case, the results are for a YOLO version 11, but we also try with YOLO 8. Of course, there are limitations, so we are having hard trouble with diffuse findings, which we believe maybe through iterative max realization or targeting the anatomical structures could be a good way to solve this. Healthy check X-ray bias, because we only use mimic CXR, so including more sources could be valuable, and there's not explicit control for size and severity. We also think there's potential to extend this framework and to also model rare cases. And these are the conclusions. So we could see actually that semi-sync CXR can generate semi-synthetic check X-rays with intrinsic bounding boxes. It can really help augmenting real training data with significant gains. Generation quality is comparable to fully synthetic baselines, and the framework is extensible to other modalities. And thank you, and I will be happy to receive any question.
Do we have any questions in the audience? Maybe I can start then. Do you have any limitations on the image quality or the image type if I want to extend this on my own data set? Maybe something that would make the method work less or differently, like image noise or something?
In terms of data quality, I think in this case the most could be that actually the diffusion model doesn't, or just learn from a different distribution of data, and then when we try to paint, it just looks weird on your image at the end of the day. But this comes at the end, more from the pre-trained diffusion model. So that's the only case that I will say, okay, it might be, or it might look weird that, for example, your image is light, and then you paint or you do an occlusion that is super strong, and then the contrast is super high. So that's kind of the case that I will see it coming from. But in general, I think not really. From the framework itself, the way also the edit works is super clean. It's you go in each of the steps of the diffusion process on the reverse process, and I think that's a really nice way, to be honest, a really intelligent way to do edits on images.
Thank you. You also mentioned expanding to 3D data. Is that straightforward to do, or is there some limitations of the models apart from memory?
Yeah, I think it's possible, but it's not so straightforward. So 2D will be the most straightforward case. On 3D, I think we will need really to think on how to create a distribution for the bounding boxes, because in this case, we are not talking on just about a square, but it will be more than probably a cube or a region. And I will say that's kind of the point where we need to think a little bit more about.
Thank you very much.
Thank you.
Let's thank the presenter again.
All right, and we will have our last full oral presentation for the session, which is presented by Febrian Kartika, Efficient Self-Supervised Adaptation of 3D Abdominal Vision Language Models for Institution-Specific HCC Classification via Full Fine-Tuning and PEFT.
Good morning, everyone. Thank you for the introductions, and thank you for coming here despite the harsh weather. My name is Febrian. I'm going to present the efficient self-supervised adaptations of 3D abdominal vision language model for institution-specific HCC classifications, and we compared how full fine-tuning and PFT performs on these classifications. So as a motivations for this study, as we all know, Vision Language Foundation model has shown a pretty strong performance without using any labels. When it's trained contrastively using self-supervisions. But the limitations here is that we always need hundreds, millions of data to pre-train this model, and then it's very prone to overfitting if we use a small set of data set, and then it always uses a huge computing powers, hundreds or couple GPUs at least, and for some hospitals or some labs, these resources are not always available. So that's when we discovered this Merlin Foundation model. What we found pretty interesting about this VLM is that it uses a 3D CNN instead of a vision transformer, which most VLM use. And this really helps with the efficiency since 3D CNN is way lighter compared to vision transformers during training. We mostly follow the part A of the Merlin training strategy, but they use phenotypes to sort of weekly supervise the training of their models. But in our data set, we mainly use the image and text report paired, not the phenotypes. So we have a set of HCC positive of specifically venous face CT scans and also a non-HCC venous face CT scans. Now, the negative part is not a healthy abdominal scans. Instead, it's a negative group includes patients who do not have HCC cancer and may exhibit other hepatic pathologies that could plausibly confuse the model, such as the fatty liver or hepatitis and other benign findings except HCC. And then we paired this also with the radiology reports, such as the findings and impressions and the anatomical part as the examples above. And to compare it with how Merlin performs on our data set, this is the zero-shot cosine similarity matrix and also the embeddings. And as we can see, it's not performing pretty well in this case. So our methods is to try to fine-tune this and then compare how the full fine-tuning and PFT, we use convolution LoRa and also LoRa for the text encoder with the final projections, layers, and frozens. Above that, we also try to analyze how the temperature would affect this fine-tuning, as temperature is one of the key parameters in info NCE loss, but is, I would say it's a bit understudied in this case. So our initial results show a very promising performance. We only use around 2,000 training data compared to Merlin's pre-training of 15,000. That's only 13% of the data. And using PFT, we can train this using only a 20 gigabytes of GPUs. And as we can see from the table here, using a higher temperature yields a better performance compared to the lower part of the temperatures, which then we realize that the temperature initializations affects how a VLM fine-tunings fine-tune significantly. We also plot this temperature analysis comparing from the lowest temperature on the left-hand side to the highest temperature on the right-hand side. And we can see how significant the difference is when the model is trying to classify between an HCC and a non-HCC classes. To further test our model, we also perform this qualitative analysis on GradCam. We can see that after fine-tuning, the model focuses more on the liver part side instead of the other anatomical regions part. And analyzing the loss, we can see that the higher temperature on the right side here, during fine-tuning, it's less prone to overfitting compared to the very low temperature of 0.07, which what CLIP actually uses as their pre-training. So with a lower temperature, it almost overfits instantly after a couple of training epochs. But with the higher temperatures, the model can adapt pretty smoothly compared to the lower temperature. So The higher temperature naturally acts as a regularizer during this fine-tuning, which enables the model to tune more smoothly. So to further test our model, we perform a sensitivity analysis, but we found that both our models is pretty sensitive to the length of the CT scans due to the nature of our datasets, which we tested. If we play around with the length of the CT scans, the performance drops significantly. But yeah, to mitigate this, we try to crop our dataset and to sort of average between the positive and negative scans. But following Merlin's data processing, we interpolated to 224 by 224 by 160 instead of zero padding like Merlin. And you can see from the comparison of our slices and Merlin average slices is that our slices is less rich in data compared to them, which increases the difficulty of fine-tuning this model efficiently. Yeah, so just for comparisons, so for the original dataset and the retrained crop dataset, on the Merlin side, the accuracy and AUC dropped, and there's an increased recall since the zero-shot model mostly predict the positive part. And on our case, we have an increase about 20 until 30% in accuracy in both PFT and full fine-tuning respectively. Also a 10 and 20% F1 score improvement from the pre-trained Merlin model. And then, yeah, we just want to mention that our finding still holds given the difficulty of the task as well with the less richness of the data set and yeah. For comparison as well, the right lower side of the table here shows that with PFT, we can see that the performance on the external versus spine fracture data set still holds compared to full fine-tuning, which has dropped to 0.35, which also means that PFT helps with preserving the previous knowledge of the learned data set of Merlin. So yeah, we plotted this temperature analysis as well, and as everyone can see as well, that the higher temperature still preserve, the higher temperature still able to adapt compared to the lower temperature, which completely fails to adapt to our data set. So to conclude this work is that to fully fine-tune VLM efficiently is definitely feasible, even in difficult tasks like an ACC classifications. And then temperature ionization affect the performance and training process significantly, where lower temperature over-penalize the loss by a significant value, leading to a very quick overfitting to a small data set like in our case, where a higher temperature allows the model to slowly and gradually adjust to the data set. And then resampling, padding, and cropping the dataset to the same shape might still introduce some unintended bias in the dataset. So for future works, we should focus more on the multi-phase dataset, since this work is currently only focusing on the Venus phase. And then also multi-class classification should also be explored, as the current work only works on binary classifications, and there's also other efficient fine-tuning method other than LoRa and convolution LoRa, such as prompt tuning, VPT, and yeah, other efficient tuning should be explored. That should conclude this presentations. Thank you.
Thank you. We have time for multiple questions. If anyone would like to approach the microphones. But I can start us off. So thank you for a wonderful talk. That was very interesting and I think relevant to many of us doing model fine-tuning. I found the interaction between the temperature and the parameter-efficient fine-tuning really interesting. Maybe you could speak more about that. Do you think that doing this parameter-efficient fine-tuning affects the hyperparameter temperature choices that you have made?
Well, we tested on both full fine-tuning and the PFT, and the temperature acts similarly in both fine-tuning methods. So I think in terms of temperature, it doesn't matter whether you tune it using a full fine-tuning or a PFT, but the temperature still acts as a regularizer to the fine-tuning methods. So it acts to sort of gradually smooth the training performance overall.
To follow up on that, yeah, that's very interesting because you also found that there's a protective effect of the PEFT preventing some overfit. And so maybe you could speak more on that. Why do you find that what do you think causes this to happen besides just the low rank assumption smoothing things out? Or is it that we need to assume some type of regularity?
So in PEFT, it causes less overfitting since we doesn't train on all the model architectures. Instead, we just injected some parameters and then fine-tuned that, which also limits how the model can learn and adapt to a new data set. So if we couple that with the temperature analysis, there's always a number, a perfect number where you should initialize your parameter, but obviously that's not easy to find. It took a couple of trial and errors before finding the perfect numbers. That's why we compared 4 different parameters from a very low to a very high temperatures. And yeah, PEFT itself, if coupled with a pretty high temperature, it would limit how the model could adapt to the data set. So if we do more adjustments on the, how many alpha or rank in a PFT and how low or how high the temperature, it might even, increase the performance even more compared to now. So, yeah.
Thank you. And let's thank the speaker again.
Thank you.
So now we will move to our our spotlight session, where we have 4 talks, and I believe that they will introduce themselves. So.
Hi everyone. Today I will present our project, SCR2ST, which combines single-cell data with spatial transcriptomics for efficient active sampling and expression prediction. Spatial transcriptomics tells us not only which genes are expressed, but also where they are expressed in the tissue. However, this powerful technology comes with a major limitation, which is cost. The cost becomes high because current ST experiments usually follow a fixed grid sampling strategy. When the tissue area is large, this strategy requires sequencing many spots. However, many neighboring spots may come from similar tissue regions and contain redundant biological information, so the cost keeps increasing, but the biological return does not always increase proportionally. This motivates us to use single-cell or NSEC as prior knowledge. Single-cell data can be viewed as transcriptomic profiles without spatial coordinates. Over the past years, large-scale single-cell resources have accumulated rich information about cell types, cell states, and biological diversity. Therefore, instead of sampling spatial transcriptomics blindly with a fixed grid, we use single-cell knowledge as a biological reference to guide where we sample in tissue. Here we introduce SCR2ST, a unified framework with 2 major components. The first component is single-cell guided active sampling. The second component is SCR2Net for expression prediction. Now let me briefly introduce the active sampling module. We first divide the whole slide image into dense candidate patches, where each patch represents a potential sequencing location. Then, visual features are extracted from these patches using a foundation model and passed into a lightweight policy network. Instead of directly making hard selections, the policy network assigns a sampling probability to each candidate location. Based on this probability distribution, the model selects a small set of spots in each round. This process is repeated under a fixed sequencing budget, so the sampler can progressively identify more informative regions while avoiding redundant sampling. After selecting informative spots, we further use them for gene expression prediction. Our model includes a regression branch to learn a general image to expression mapping, and a retrieval branch to bring in expression information from similar reference spots. Importantly, single-cell priors are used to filter unreliable retrievals, making the prediction more robust under low data settings. The results show that SCRL achieves better sampling efficiency. The reason is that our sampler does not select spots blindly. By incorporating single-cell priors and spatial constraints, it focuses on informative cell types and cell states, while reducing redundancy in neighboring regions. As a result, even with a small number of sampled spots, SCRL can capture meaningful biological variation. SCR2Net also improves expression prediction performance. The regression branch provides a stable global image to expression mapping, while the retrieval branch brings in additional supervision from similar reference spots. Single-cell priors further filter noisy or biologically inconsistent retrievals, making the prediction more accurate and robust. In conclusion, SCR2ST makes 3 main contributions. First, we propose a unified framework that integrates single-cell prior knowledge with spatial transcriptomics for efficient sampling and accurate prediction. Second, we introduce a single-cell guided reinforcement learning strategy to move beyond fixed grid sampling and actively select biologically informative and spatially diverse regions. Third, we develop a hybrid regression retrieval prediction network, where single-cell priors improve retrieval quality and enforce biological consistency.
Hi, everyone, I'm Yaming Li from Nerdy Lab, Vanderbilt University. I'll be presenting Unibolt, a unified model that translates scaled EEG into fMRI signals and further reconstruct the functional connectivity. So why do this at all? fMRI gives us whole brain dynamics and connectivity, but it's expensive and immobile. EEG is cheap and portable, but spatially blurry. EEG to fMRI translation tries to get the best of both, fMRI level insights from the cheap portable recording. EEG to fMRI translation has been attempted, but prior work leaves an important gap to be filled. State-of-the-art method like Neurobolt train a separate model for each brain region, which doesn't efficiently scale to the whole brain. Only the handful of regions were evaluated. Functional connectivity was not assessed, and eyes-closed resting state was still largely underexplored. That's what we aim to address here. Here's the model at a high level. Unibolt has three main components: a multidimensional EEG encoder, an adaptive multi-region decoder by which all brain regions can be predicted in one forward path, and a multi-objective loss. The loss combine MSE with the temporal and spatial correlation terms, so the prediction preserves both fMRI dynamics and inter-regional structure. Okay, so does giving up the per-region model cause us accuracy? The answer is no. On the left, our unified model in red matches or beats the RI-specific baselines in blue. On the right, we can see that the submental motor network is the most predictable, followed by dorsal attention and visual networks. We next aggregate RI predictions into network-level time series using the functional network assignment. The result here shows that Unibolt captures meaningful large-scale brain dynamics, not just RI-wise correlations. Beyond time courses, to our knowledge, this is the first EEG to fMRI model evaluated on functional connectivity recovery. Here we compare the ground truths and predicted connectivity matrices across different sparsity ratios and 3 parcellation scales. We can see that the connect-closed network block structure is clearly recovered. And our model generalized. We trained our model only on resting state data and test zero-shot on an arbitrary test dataset from a different state and different scanner. Using only 23 shared EEG channels, it transfers well out of the box, and fine-tuning pushes the performance even further. Overall, this study advances EEG to fMRI translation through a framework for efficient whole brain reconstruction of fMRI signals as well as functional connectivity. Thank you all for listening. Please visit our poster for more details, and you're very welcome to reach out if you have any questions.
Hello everyone, my name is Zheng Zheng from the Department of Computer Science and Engineering at the University of Texas Arlington, working with the SMILE lab. Today, I'm very glad to present our work at the medical image with deep learning, MIDL 2006, titled Heterogeneous Aligned Fusion for Survival Classification with Missing Modalities. Accurate survival prediction from multimodal medical data is a very important problem for supporting personalized treatment. Existing multimodal fusion methods such as polling-based fusion, attention-based fusion, and linear interaction-based fusion has shown promising in medical prediction tasks. However, most of them do not explicitly address the two practical challenges. First, modalities are heterogeneous. Their representation often lie in incompatible feature space, leading to missing alignment. As shown in left side TSA in visualization picture, features from different modalities are clearly separated. Second, modalities are often missing, which can cause unstable prediction. So the key question is, how can we achieve the reliable multimodal prediction under missing and heterogeneous data? To address those challenges, we propose the heterogeneous aligned fusion, a 3-stage framework. In stage 1, we extract the embedding independently from each modality. In stage 2, we align all modalities into a shared latent space by getting them toward a dominant direction. In stage 3, we enforce that using more modalities should not degrade the performance. This design enables both alignment and robustness into multimodal learning. More specifically, we introduced two key components. First, global alignment, which reduces the discrepancy between the modalities and encourages them to share consistent representation. Second, monotonic fusion, which prevents performance clips when more modalities are introduced. Instead of blindly using all modalities, the model learns to rely on stable and reliable signals. We evaluated our method on hand-coded dataset. Compared with existing multimodal baseline, our HAF achieved the best AUC while maintaining the strong accuracy. In particular, global alignment improved the representation stability, and the monotonic fusion reduced the effect of noisy modalities. We further evaluated robustness under missing modalities. As shown here, both AUC and accuracy remain stable even when modalities are randomly dropped. This demonstrates that HAF is robust to incomplete clinical data. We also visualize the effect of alignment. After applying global alignment, the discrepancy between the modalities is significantly reduced, indicating that they are better aligned in a shared space. In summary, we propose a heterogeneous fusion framework that aligns heterogeneous and improves the robustness under missing modalities. Thank you.
Hi, I'm Matthias Heinrich from the University of Lübeck, and I'm happy to present From Surface to Viscera, 3D estimation of internal anatomy from body surface point clouds. Medical imaging excels at looking inside the human body. However, this clinical power comes at a heavy cost. Very high equipment expenses, and in the case of CT, ionizing radiation. And there's a hidden bottleneck. Today, manually setting up a patient and selecting the precise field of view takes up the majority of the absolute scanning time, and an underutilization of expensive CTs and MRIs. If the positioning is slightly off or the field of view is misjudged, this comes at an even worse outcome and results in time-wasting rescans and unnecessary radiation dose to the patient. So we asked, what if we could predict internal anatomy before the patient even enters the scanner bore? Depth cameras are cheaply available, and they can instantly map the accurate 3D external shape of a human. To bridge the gap from this external surface to the internal viscera, we leverage the power of large-scale deep learning. By training on a massive public database, here a German national cohort, which features tens of thousands of whole-body datasets of MRIs, we can accurately learn the complex hidden statistical relationship between external body shapes and internal organ topography. And to achieve this mapping, we introduce a new approach, the forming point transformer. Instead of predicting organ anatomy from scratch as a regression problem, we use a point transformer that learns to deform a statistical mean shape model of internal anatomy. By formulating the problem as a template deformation conditioned on the external point cloud, our network can use KNN neighborhoods from the sparse surface data to accurately achieve this, and also use efficient local self-attention. The result is a method that is both highly robust and highly accurate. It enables real-time 3D estimation of internal organs and opens a door to fully automatic zero-dose patient scan positioning. The quantitative results demonstrate clear gains over previous methods, such as point convolutional autoencoder, across 20 challenging internal structures. And this has been a joint effort from the University of Lübeck, Fraunhofer-Mewis, and Philips. Our code and models are publicly available on GitHub. Thank you, and see you at our poster.
Okay, so that concludes our spotlight presentations. At this time, I believe we're handing this off to Youngmin Jin to introduce our keynote speaker. is Youngmin Jin.
Good morning. Thanks for sticking around for the impending storm, I guess, that's on the way. I was supposed to have lunch with my parents after this talk, because my parents are actually, they grew up in Taipei, and they're visiting Taipei from LA. And yesterday morning, as I wake up and I'm due to board my flight to Taipei, I get an email from the airline that my flight tomorrow is canceled, and so I'm leaving like right after my talk now to go right back to Singapore. All right, so for those sticking around, glad that you made it. And it's still sunny outside. We'll see how long that lasts, all right? So thank you, Yueming, for the kind intro, and thank you to the organizers for having me. And since we're starting a little bit early, I'm just gonna expound a little bit on the importance of what you all do. I think we know that this is a medical imaging conference as it relates to AI, deep learning, et cetera. But my talk today doesn't in particular revolve around imaging, but I think it will hopefully highlight the importance of imaging and where the field of not only healthcare is headed, but where health is headed. Right now, I think a lot of how we think about imaging is to find disease, to help make sick people healthier again, or to address dysfunction. But as I'm sure all of you know, how consumer health is evolving, how imaging is evolving, where you're starting to see people want to peer visually into their health earlier, how access is being made available earlier. Hopefully you'll see opportunity for what you do becoming even more relevant. We know it's very relevant already, but even more relevant to more people. And so I wanted to kick things off by thanking all of you for what you do, because trust me, given the inquiries that I get on a weekly basis for people asking for access into their own physiology and anatomy earlier, mostly coming from people who are healthy, I think you'll see a lot of work to be done in the field. So thanks to you for all that you do and what you will do. And let's get things started. So I'm gonna kick things off here with a question to everybody, which is your health a story or a snapshot? I think most of you have been to a doctor annually to do a health check. And for those of you who are based in Taiwan, you have an internationally renowned national healthcare system where annual health checks are super accessible, and we know that, as well as probably many of you from other parts of the world as well, and to those of us hailing from Singapore. But the way that our health is explained to us now is a snapshot, right? The doctor reads your blood panel, and they tell you to sleep more, drink less, eat healthier, exercise more, and I will see you 365 days from now. And maybe if you don't do your health check once a year, they'll see you 1,000 days from now. Who knows, right? But right now, your health is represented by snapshot. And the challenge there is when we think about even healthy people, and certainly diseased people, when they're on medication, the optimal dose of a medicine changes over time. But we actually view optimal dosing by snapshot. The right dose for a person on a Monday can be very different the following Monday, even a few hours later, but we would never know. When we represent health by snapshot, we miss a lot. All right, so then the next question I have for you is, are you an N equals to 1 or are you an average? Because healthcare right now is represented by average. Everything is derived by average. The doses we take derived by average. The reference values of those blood markers I talked about derived by average. And I will argue none of you are average, right? None of you, right? But healthcare that is built for you is derived by population and is implicitly not built for you. And we can talk about scalability, which we will, but if you ask 100 doctors today, should medicine be precise? Should it be personalized? I think all of them will say yes. But then if you ask them, what about N equals to 1 medicine? They'll say, oh, but that's a case report. It's a one-off. It's anecdotal. So I think there's a conflict between what our medical system really wants, how it views itself, what you actually are, and what we're actually delivering. Right? Because I don't think it's fair to just say, well, N equals to 1 will never be scalable. So let's just keep on with the average. And then the next question is, there's a lot of talk right now about our health care needing to be more longitudinal, but I don't even think that's defined properly. Because if you take your medical checkup data from once a year and you collect it for 10 years, is that sufficient? Is that useful? Or is that just 10 snapshots? Because I can assure you, there are things that happen with your anatomy and physiology that occur at time scales that matter, that can be informative, that happen way more frequently than once a year. I have a friend. He is a billionaire. He has unlimited access to the type of health care he wants to fortify his health. And he's having a team of people build algorithms for him to aggregate all of his data. Everybody who wears a wearable, go on LinkedIn, there's these amazing one-line headliners saying, now this wearable is going to start integrating your electronic health record. But what's in your electronic health record? My buddy who's a billionaire, I asked him, I said, how many LDL readings do you have in 10 years? And he said, and he knows his record. He said he had about 8 readings in 10 years. I said, what do you expect to learn from aggregating your LDL readings over 8 markers, other than that it just keeps going up over the years? And then maybe if you take a statin, it goes down. What will you actually learn about your intra-individual dynamics? Right? If you're defining longitudinality as once a year for 10 years. And so largely, as I mentioned, medicine is based on averages. And in the evolving field of healthy aging, longevity, Taipei, we actually do a lot of work just north of Taipei with our team in Singapore because there are really interesting aging dynamics happening in the world right now where we know that seniors are living longer. The last decade plus is in relative poor health, but now also young people are getting sick earlier. And at the same time, young people are very open to understanding and engaging with their own biology, but the problem is the longevity field as it grows is largely conventional medicine with redefined as longevity, a risk score. You know, you go to a young person who's 30 years old and you tell them, look, based upon your biomarkers, you have a 20% chance of coronary disease by the time you're 60. That's what they do now in healthcare, right? They use algorithms which are snapshots based on bigger snapshots to give you a risk trajectory, but going to a 30-year-old and telling them 30 years later they might get sick, and by the way, 20% is not great, right? But to a 30-year-old, hey, 20% I get coronary or cardiovascular disease, 80% I won't. 80% is bigger than 20. I'm great, I'm doing well. We know that that's too abstract, so now the longevity field is rebranding a risk trajectory as biological age. You're 30 years old chronologically, your biological age is 28. Go home and eat some pizza. Go eat some fries because you're younger than you really are. We haven't really deciphered how to properly do this yet. And then, of course, things like maximum tolerated dose, all derived by average. Even drug synergy is derived by average. So now, the next iteration of longevity, it hasn't even sorted itself out yet, is now moving to AI and longevity. Right? But if you look at a lot of the work in that space, there is no AI in that space at all, right? It's just people talking about the potential of it. But I can assure you, if you collect 1 billion snapshots, 10 billion snapshots, you still got to know the story. We are all different from each other. So those snapshots will give you insight for that. But we are different from ourselves over time. And if we don't capture that type of data, no AI will tell a story at a population level or at an individual level. So if in fact our health is a story, it's not a snapshot, then optimums, precision, personalization are dynamic processes. They are not static. And what pains me right now is we're largely using these one-liners. The future of health and healthcare is predictive, preventive, precise, and personalized, and people nod their heads. But we're not really understanding the concept that we evolve over time and our treatment should evolve alongside us. And this is where fields like imaging can matter. And I'll get into some use cases as we move along. And I want to emphasize maybe there's a little bit of a difference between how the fields converge, but what my team does, we don't use large amounts of population data to train an algorithm to treat the next person that walks in. So my team only works in the treatment realm. We don't do much in the diagnostic side, but the diagnostic side informs how we treat. So we use only a person's own data to manage only their own treatment dynamically. And this is where, and I'll give you examples later of how imaging has been profound for us. I'm gonna do 2 use cases today, 2 core use cases, and I'm gonna show you how we do what we do. My team does not deal in retrospective analysis, right? So we don't take large amounts of data, run analysis, and say, if we had given this patient this treatment, they would have responded this way. Every single day, including today, including tomorrow, our team makes drug dose recommendations to patients at our hospitals in Singapore, and we adjust those doses accordingly to make sure that they are the right doses for the patients. So I'm going to give you one use case. We're treating a rare cancer patient right now, has Waldenstrom macroglobulinemia. In Singapore, it's about 1 case every 3 to 5 years. And for rare disease, you don't have a lot of treatment options, and when you do treat, the tendency is to just treat people at maximum tolerated dose. We develop these curves, so when a person walks in the door, we have no data on this person because we're not using anybody else's data on them. We actually have protocols that let us expose the patient to variable doses of the drug that they're being given. So we vary the input, which is the dose, and we measure the change in output, which is the cancer marker, which is a very different data set than giving somebody a fixed dose and then tracking their biomarkers over time. Longitudinal right now is give everybody a standard of care dose and then track their markers. We actually vary the dose. If they're given multiple drugs, we can look at dose variation because we can then look at drug interaction in that individual to open up a different depth of data on this person. We create the curves, we dynamically adjust doses, we don't use genomics, we don't use big data, we don't ignore that information, but we also don't need it, we don't require it, and we're using only the patient's own curve to guide only their own care. What was interesting about this patient is whenever he would get the maximum tolerated dose, the standard of care dose, his cancer markers would just keep getting worse. No efficacy, which sadly is too common. It's very common for cancer patients. And when drugs stop working, what do? You move them to another drug, and you keep moving them to another drug until there's no more options. Max dose, no efficacy. Using his curve, we would drop his dose between 20 to 40% lower, and whenever we would drop the dose, the patient would start responding again. Okay, so max dose, no response, low dose, response. We don't deal in hypotheticals. This is not a retro, hypothetical, theoretical case. This patient, we prospectively, we only deal in the tomorrow. We recommend the dose, the doctor signs off on it. On average, from our most recent cohort trials, doctors accept about 98% of our dose recommendations. Sometimes patients get COVID, they have to hold the dose. We published an intermediate study on this patient. This study was planned for 12 months. When the patient was recruited into this trial, he was 80 years old, all right? And at present, we're about 5 years and he's still going. In fact, his cancer markers are the lowest they've ever seen. The patient no longer needs blood transfusions. We've saved him tens of thousands of dollars in drug costs. That doesn't include hypothetical reduction in hospital and readmissions due to toxicity. And we've also saved the healthcare system money because he doesn't need more readmissions as well. All right, so the patient's doing well. He has asked to remain on this trial because it works really well with his quality of life. And so we've done this, right, for a lot of indications. We discharge transplant patients. We did this with UCLA. We discharge patients about a month early compared to standard care. For those of you who are not familiar with US healthcare, one night at a UCLA ICU can be about $30,000 US dollars. For $30K, you get 4 walls and a ceiling. You don't get doctor time, nurse time, medicine, surgery. It's just the room, right? And these are very sick patients. Some of them are in ICUs for months. When you get them out a month early, you not only save on cost to patient, we're talking about getting immunosuppressed patients out of ICUs faster, which could save their life because of potential for community-acquired infection. We've dropped doses for cancer patients 50% to increase efficacy. I will note, and this I think will be relevant for the team here, but in some cases there are no markers. Okay, there are no blood-based markers for patients from which we can guide their dose. Up here was a gastric cancer patient and his cancer markers were 0, right? But he was stage 4, and because the patient really wanted to try, we used dynamic imaging as the marker. And it takes specific use cases, specific circumstances. The doctors for this patient believed the images, right? And so imaging can be, and imaging is actually the ultimate marker. All right, I'm gonna get into more of this later, but my wife is actually a brain and spine tumor survivor. And I've been talking to her radiation oncologists for years about potentially using dynamic radiation dose adjustment because that's something the field has been trying to pursue for a long time. And her rad onc had told me that they actually image her before every single session, right, to make sure that their treatment planning is aligned, they got the margins all lined up. They're very low resolution images though, right? These are not bona fide CT scans. And in her case, 36 sessions of radiation, right? But the field that I'm speaking to today is precisely the field that can make use of that information for us to definitively guide the modulation of radiation therapy, which is now just starting to see more prospective activity. In fact, the person that I brought in as a graduate student to do the drug dosing work is a person who previously was a physicist who studied imaging for oncology, right? And so for patients who are very sick, imaging now is viewed as a checkpoint to assess treatment progress or as a diagnostic, right? But the ability to leverage existing workflows that get a lot of images dynamically will be extraordinarily profound in terms of developing a new biomarker, right? A dynamic biomarker for patient adjustment. 15 years ago, when we proposed the concept of dynamically adjusting dose, I was roundly kicked out of offices, okay, of oncologists. They're like, we're never gonna lower a dose for a patient. It will be illegal, it will be unethical, it will never happen. 15 years later, the workflow for all of this is now published in the ASCO educational book, right, which is the primary resource for oncologists worldwide. And what about combination therapy? Right, we not only guide dose, we do rapid combo design for patients. No big data. We actually have to run experiments on each patient's sample or blood, and that's actually commercialized already, right? Hundreds of patients in our region were now commercialized to the US, Europe, and ASEAN, broader Asia, for solid blood, all of the above. And people ask me all the time, like, can you scale n equals to 1? It's already scaled. Right? We're like helping patients every single day now across the globe to do this. I think it's time to acknowledge that when we've always been telling patients that we should individualize their care, that we actually do it. And we do it dynamically when possible. All right, so I'm gonna switch gears. Okay, I'm gonna switch gears because at the beginning of the talk, I mentioned to you that healthcare will always need what you do. But I think so will those looking to preserve or fortify their health. Those who are interested in future-proofing it versus past-proofing it. So one big issue right now globally, and this has always been the case, is that healthy people are super efficient at becoming unhealthy. All right? That is a perennial issue. When you get your annual health checkup, the doctor tells you to do all this stuff. Healthcare is very good at telling us what to do, but it's challenging to tell us how to do it, and then more importantly, how to stick with it. Right, so then I have another question for all of you, which is engaging with your health fun? Is it fun for you? I can agree that engaging with healthcare is probably not fun, right? Like when someone's very ill, it's very hard to make that a fun process. But while we're still mobile, while we're largely disease-free, is engaging with your health fun? Is exercising fun? Is looking at your health data fun? Do you look at your health data beyond once a year for 10 years? Is it fun? Because if it's not fun, if engaging with your health is not more fun than TikTok at 1 in the morning, watching Netflix at 2 in the morning, then chances are we'll just resign to this, that healthy people are super efficient at becoming unhealthy. Because I will tell you, aging is aggressive. While disease can be aggressive, so is aging. It's happening, right? Whether we like it or not, it's happening every second I talk, right? So the second use case I'm gonna show you is actually me, okay? I initiated a trial about 2 years ago known as Delta. And I'll tell you why it's called Delta. And before anybody's curious, this trial is backed by 2 IRBs. Okay, in fact, this is not a data collection exercise. It's not the n equals to 1 that we usually think about where I just try a bunch of stuff on myself. Okay, here we go. So it is double IRB backed. In fact, we had to get even higher order approval to do this trial. And since I'm speaking to an imaging crowd here, No AI was used to modify either image, all right? This is actually me on both sides. I want to emphasize that delta is not a before and after photo. It's not a weight loss exercise. Okay, there's a lot of places you can go to lose weight. It's not what the point of this trial. In fact, I didn't even know that was going to happen. My son shares a photo album with me, and he dug these photos up and happened to find them. Our national health system that covers a segment of Singapore paid for the trial, not for people to copy what I did, right? I'm not trying to develop some sort of regimen that everybody should copy to improve their health. But the goal here was to create frameworks where everybody can find out their acute delta of specific markers to truly assess their own biomarkers, all right? So I have an error on the next slide, the title here, which is, we believe that data can drive health, not just observe it, okay? So apologies, an error there. We believe data is there to help us observe, to help us check in to see how we're doing, but we think data can actually drive people to care about their health, to enjoy engaging with it. Because right now, the only way we look at our health is by, looking at a PDF with reference values once a year. And something that I think is relevant to all of us is metabolism. If any of us want to go get an insight into our metabolism, what do? We go to the doctor, they draw your blood, and they give you like one number, right? They say your blood sugar is normal. And in most of the world, if your blood sugar is normal, the doctors don't look at your insulin. And since we're in Asia, and since we're in Taiwan, and since I'm living in Singapore, one of the biggest issues there is we specifically have the genetics to have normal blood sugar, but highly dysregulated insulin. And we don't find out till it's too late. So I set off on the Delta trial, and I started looking at the dynamics of my sugar and fat burning within even one day. So that's one day over there, and the black is sugar, blue is ketone, which is a byproduct of burning fat, to kind of understand how these dynamics can actually represent not a status of our metabolism, but the functional capacity of our biology. We never assess function. We just look at status through one data point. And then I proceeded to repeat this. I started noticing these repeatable patterns. So I repeated the readings on a daily basis for a while. And then we ended up publishing the results in an earlier paper where I do disclose, by the way, that I'm a test subject in this paper. I actually sent this paper to my health insurance company, right? And I told them, you should give me a discount, okay? You should give me a discount on my premium because this information is actually super useful, and it's been 2 years and I'm still waiting on a reply, all right? So I don't think they'll ever get back to me. But in any case, they're starting to think about it, okay, which I'm happy about. But this is a lot more, right? People tell me all the time. People tell me all the time that, Dean, the only way you're doing all this is you are so disciplined, nobody can match what you do. And I counter them with 2 rebuttals. If I was that disciplined, there would be no before photo. That's the easy rebuttal. But more importantly, if you want a non-scientific third-party proof that it wasn't disciplined, when I first showed that before and after photo of me, somebody in the audience knew my dad. And he took a photo of that, sent it to my dad. My dad WhatsApped me the photo and was like, where was all of this discipline when you were 18 years old? All right, so it was a non-scientific feedback that it wasn't the discipline. I never knew that my data was so straightforward to look at. I never knew that I had this degree of control over my own biology. And over time, my ability to switch between energy sources, and that's actually what your metabolism is, started speeding up, right? This is like metabolic fitness. We don't know any of that stuff right now. We just look at one number, right, which is constantly changing. And there are easy ways to get this done. So in my limited time left, I'm going to fly through the remaining aspects of my own story, and because the ultimate objective of what I did was to look at metabolic resilience, and I'll define what that means. And so over the course of the work, I've started looking at sleep data, right? And when I start thinking about a lot of this, right, I start to think about how there are potentially even other ways to assess the impact of sleep intervention on whether it's anatomical or physiological change. On the left, I have data which I fear is relatable to many of you, which is I used to sleep at about 2 in the morning on a regular basis. And I would try to wake up at about 8 or 9 to try to mathematically achieve 6 to 8 hours or whatever of sleep. But my actual sleep was about 5.5 hours. When Delta started, I adjusted my sleep from 2 a.m. to 9:15 p.m. And I'll start off by saying none of you have to sleep at 9:15. I'll tell you later why I picked 9:15. But when that happened, if you look on the top, you can see this objective consolidation of my deep sleep. At one point, my deep sleep tripled. And I wore like 3 wearables for this study for like a year, okay? Longer than like these 1-week things that people are posting about. And my resting heart rate went from 65 BPM at the start of the study to about 46 BPM, right? And it's still going. My gut, I think I have the most widely studied gut in Asia, okay? My gut, I've looked at the gut dynamics. I'm gonna skip all that just to say that our guts are very dynamic, but I'm gonna talk about this part here, which is fusobacteria. Fusobacteria is a bacteria where you don't need 0, but fusobacteria is associated with type 2 diabetes, fatty liver disease, colorectal, all of the above. And when you look at the population, which includes Singapore, Malaysia, Indonesia, Vietnam, Thailand, Taiwan, et cetera, where this study's been run, fusobacteria is prevalent. It's quite prevalent. And what I'm starting to see on social media from young people in particular is they're starting to post, and you know, it's pretty interesting, right, that people are being more open to share their data, as I'm doing right now, but I'm seeing fusobacteria that comes up to like here, right? They're putting their data out in public, and I think we'll come to see that we're gonna start to see more preemptive opportunities to help people. Not even just from medical imaging, but from understanding data as we see it in this format as well. Right? And when I look at the journey here, and today I'm showing you like 1/100th of what Delta included, but I ultimately ended up stepping up and doing insulin dynamics analysis because I never looked at my own insulin. My blood sugar was always good, but I never looked at my insulin under stress. Fasting stress, exercise stress, poor sleep, good sleep, all of which are known to impact insulin. And so I ended up doing an insulin dynamics test. And when I did this blood draw, the last blood draw here, my nurse told me that she's drawn my blood 50 times, okay, in the last couple of years. Nobody needs to draw their blood 50 times either. I did it because I did repeats. N equals to 3 minimum, controls, I did all of that. And she told me, she's like, I drew your blood 50 times. I've never looked at my own blood work. And she actually discovered she was insulin resistant after she drew my blood. And she actually, the day before that, she felt, the week before that, she felt faint after eating lunch. So she did an insulin test, which she had never done actually, because her blood sugar was normal. And she discovered she was insulin resistant, but she is young enough to do something about it, right? And so dynamics matter. And if we don't even look at the dynamics, we miss a lot of things that can otherwise help people. And so I learned from this that my insulin is actually now lower than my kids, okay, who are 12 and 13 years old. And because young people are getting sick earlier, something that matters for us, all right? This is, I think what I present is a little bit different than what's being talked about, but I want to say that there's a lot of opportunity to start leveraging what you've done to keep healthy people healthy. Because a lot of what we do, and we should continue to do, is focused on those who have dysfunction and those who are sick get better. I think we'll never stop doing that. Neither will our team. But I think that what we have with people starting to be more open to whole body MRI scans, which lots of people think different things about that, but doesn't matter. It's going to happen. It's happening already. There's a lot more that's out there for us to work with. All right, so I'm going to close by answering why I sleep at 9:15. Right, I sleep at 9:15. Again, none of you have to sleep at 9:15, right? But is because my kids sleep at 9:15. My kids are 12 and 13, as I've mentioned. And at 12 and 13, their friends, I can track when their friends message them on their phones. Their friends sleep at 1 a.m., 2 a.m., 3 a.m., 4 a.m. My son has friends that pull all-nighters on a fairly regular basis. And we know that young people are getting sick earlier, right? And when I say young people, that means all of you too, by the way, all right? So insulin dysregulation. We have people that don't know that when you sleep too late, your insulin starts to climb, right? And we have people that, that undertake habits that very clearly drive insulin up. So as I mentioned earlier, my wife is a brain and spine tumor survivor. She was diagnosed about half a year after we moved to Singapore. And as she was battling her way back, I was basically plunging this direction. And our kids were 4 and 5 years old at the time, right? And when you're going through that, and these kids are 4 and 5, at the time, we were eating McDonald's like 2 to 3 times a week, and the kids are 4 and 5. They eat what we put in front of them. And when I started engaging with my own data, I started to understand how what I did was impacting not just myself, but those around me. And my wife, by the way, that photo was taken only a few months ago. She also had a spine tumor, as I mentioned. So she was actually paralyzed for a couple months, and she's like a 5-time full marathon runner, right? And so we talk a lot about what we do very discreetly, right? We look at a person's data. There's a lot that we look at, but when we start to move earlier in the life spectrum in how we help people, I think it's important to note that if your work goes on to help a healthy person stay healthy, you're actually helping a lot more than just that one person, okay? Because when you deal in that specific domain of people who are still healthy, this is well known over like decades of behavioral sciences research. Healthier parents have healthier kids, healthier doctors have healthier patients, healthier leaders, and many of you are leaders in the audience. Healthier leaders have healthier team members, and healthier friends have healthier friends, right? So we all deal in data. We deal in data in different formats, but a lot of people can be helped by what we do, and the earlier in the life course we help them, actually the more people we help. And so my kids still sleep at 9:15. They sleep at 9:15 because I sleep at 9:15. And because they still stick with it, I still stick with it, right? So it is indeed a circular process. I merely show this figure here because the number one question I get very often is, Dean, are you happy? And as a scientist, and all of you are researchers out there, that's a very hard question to answer because I have no p-values or error bars on my happiness. I have no data. Okay, actually, I have some data. I've done some qualitative research. Because people think, when I'm like eating healthier, sleeping earlier, life must be really boring, okay? But I'll tell you, balance matters. I really did eat those ice cream cones, okay? I didn't take a photo and like give one to each kid or throw them away, right? Balance does matter, but people never asked me if I was happy in the before photo, right? When I was doing McDonald's twice a week, or maybe more often, right? So everything is balanced. Longevity, in my opinion, is a personal experience. It should be personalized, and we now know what personalized means, but it is a deeply personal experience. But I want to conclude with, we do share a lot of what we're doing. We're launching trials all over the world now because Delta is expanding to more people. But again, wanted to thank the audience for what you do, because as you start seeing an evolution in how not only healthcare is evolving, but how health is evolving, you will clearly find, if not already, that your work is going to be profound in terms of helping healthy people stay healthy and those around them stay healthy as well. So thank you for having me. I don't know if we're doing Q&A, but happy to hang out before I fly out. Enjoy the rest of the meeting. Thank you.
Okay, so thanks for the inspiring and wonderful talk. So do we have any questions? Yes, please.
So thank you for coming to speak to us. Yeah, I really respect all the work you've done, and also especially the dosage control, this long-term control theory type modulations. Along that line, at the high level, you're proposing changing a lot about people's behaviors. And behavioral controls, both my own choices, maybe, or you trying to influence me or somebody else, those interfaces are quite large. Whereas, therapy control, maybe I have two variables, right? I push up on one, I push down on the other. It's quite low dimensional and maybe nice and easy to explore, or maybe not easy, but a lot easier to explore than a high dimensional interface. So do you have thoughts on how we can do that efficiently and ethically and
Thank you.
Nicely, yeah.
That's a great point. Thank you for bringing this up. Human behavior is the hardest thing to deal with across the board, not only for health, basically for everything. And we've been trying for, who knows, right? Hundreds, thousands of years to address human behavior. And I think that beyond getting into the multi-dimensionality of it, which I totally agree, I think the way the system is built is not, it's built to recognize the difficulty of human behavior, but I think that there is a gap, there's a misalignment of how innovation or strategies are built to understand the individuals that they're trying to help, of which there are an infinitely diverse set of individuals. So if you look at our team at the Institute for Digital Medicine 5 years ago when we were first started, we were mostly engineers, clinicians, scientists. If you look at our team now, we're actually mostly behavioral economists and behavioral scientists. And if you look at our collaborations, they're still largely medical, but now I advise the C-suite of a huge hospital infrastructure in Singapore. And a question they just asked me at our last meeting was, what is the most surprising collaboration or hire that we've made in recent times? And I'll tell them, hands down, we work with people from Lucasfilm, all right? Lucasfilm, I presume most of you will know, Star Wars, the whole thing. Lucasfilm used to have a major office in Singapore. And that office did animation for Star Wars spin-offs, some of the Avengers movies, and they did ABBA's Return, the hologram version, right? And people will always ask me, they're like, why would digital medicine people work with Lucasfilm, right? And I told them, I said, health is not fun. If you start delving into saying we're going to change people's behavior, it's at that point, even I am like, it's a lost cause. But areas that we do know can drive certain behavior will be pertaining to areas that we think have nothing to do with health. And you still can't conquer, not everybody likes Star Wars, okay? And, but there are levers to work with that can get people to make change, at least at a ground level. And so we're starting to do more work in fun, okay? And I think that, especially in health, if health is not fun, in health research, you can publish high-impact papers as you should. You can run randomized controlled trials as you should. You can get p-values and AUCs that are defensible, which comprise evidence, and we should always do this. But if we're saying that information, which is important, by the way, critically important, will resonate with the guy who you cannot pay to get on a treadmill for 5 minutes, then we gotta create the bridge. We don't ignore that, but we gotta recognize that there's something more that we gotta do. And so we're trying to leverage institutions that know how to do this, but not for health necessarily. Final thing I'll mention is about a month ago, I was in Los Angeles for the National Academy of Inventors annual meeting. And I frankly missed most of the sessions, but I went to one because Disney Imagineering was running that session. And Disney's most decorated inventor was speaking. And a lot of my colleagues are like, why do you want to go to a Disney Imagineering meeting? Are you like 12 years old again? I'm like, guys, hear me out. Go and talk to these people because they deal in emotion and they deal in behavior. And it turned out that whole talk was about behavior. It's overly simplified from my side, and I went up to the guy and I was like, look, I love Disney. People who know me know I go to Disney's all over the world, and I also go there to look at people. And I was there. I was in Hong Kong Disney a couple months ago, and I was, noticing that there was a couple there that was easily in their 70s. And I could overhear them, and they traveled there from the US. They were not healthy, okay, knee braces, et cetera. And then I went to the Disney guy months later, and I said, you cannot pay people to exercise. Can't do it. Right? We've known that from research for decades. But people pay you to walk 20,000 steps a day, right? People pay, in some cases, thousands of dollars to go and do 20,000 steps a day at a Disney. And then I just got back from LA Disney, actually, a month ago, and this couldn't be scripted better. My last night at Disney, I was with my daughter. My wife and son couldn't hang, okay? They were done after like 12 hours. Still a good effort. And I'm walking with my daughter, I'm like, you see that couple in front of us? They were at least 80, maybe even older. And the husband was wearing a walking boot, okay? No cane, and he was basically limping at 11:30 at night, right? And I told her, I was like, that is behavior. Now, we can't put a Disney in everybody's backyard, okay? It's not gonna happen. But leveraging emotion, nostalgia, memory, et cetera, I think that we maybe could think more deeply about how to bridge technical innovation with resonating that with the people. And that alone doesn't reconcile multi-dimensionality, but there are people that have lived and breathed how to make people feel a certain way as part of their core portfolio. So actually we're starting to engage this crowd more. Final thing I'll mention is it's not that far off. When you talk to an Imagineer at Disney, they tell you like they've been doing amazing robotics research for decades. But they have an added responsibility and job to cover up all of the cool stuff they do with fairly, still not simple, but fairly forward-facing cartoonish stuff, because their job isn't the robotics at the end of the day. It's to allow the person viewing that robot to not think it's a robot. Right? And that's what gets 85-year-olds with walking boots to be walking there at 11:30 at night, right? So I think that the field is always going to be rooted in innovation, in data, in evidence, in defensibility. But I think in this day and age especially, we can do more to relate what we do to the people we want to serve. And that may entail you interacting with social scientists, cartoonists, filmmakers, who knows? Great question. Thank you for bringing that up. Thank you. Other questions? I don't know if I ran out of time by answering that one question, but
any more questions?
and I'll stick around for, I think there's coffee and posters like right after this. I got 10 minutes, I think, before I'll hang out. Anybody who wants to talk? But again, I want to conclude by thanking all of you. Your work is deeply important and will only grow exponentially and beyond in impact. So thank you all. Enjoy the rest of your time. Thank you.
Yeah, so let's thanks for the wonderful talk from Peking Hall. Yeah, so this is basically ending our keynote session, and then we will also have our poster session. So thanks again for attending this keynote. Thank you.
Hello?
Yes.
So good afternoon, everyone. Welcome to session 3B, Anatomy, Pathology, Deep Learning Technologies, and the Clinic Applications. Our first speaker is Louis Galley, who is going to present Funny Nodules, a customizable medical data set tailored for evaluating explainable AI.
Do I have to push anything, or do I have to push anything? Or? No. Yeah, thank you very much for the introduction. I'm very pleased to present our work today here at MIDL. So in the last years of my research, I always wanted to solve this issue. We want doctors to use our AI models, right? And for image diagnosis, this means that an AI model gets an image, and then the AI model makes a diagnosis prediction. The question is now, what should the doctor do with this predicted diagnosis? Should the doctor just adopt this prediction? Well, this can be fatal because we all know AI models can be wrong, even if they have like a very good test accuracy. And even if they are right, they could be right for the wrong reason, which opens another box of problems. So the doctor has to be enabled to validate this predicted diagnosis. The AI model, therefore, does not only have to predict a diagnosis, but also it should explain why it came to this prediction. And I built models that kind of should reflect this decision-making process. And in order to know how the radiologists come to a decision, let's look how they do the diagnosis. So if they predict, or if they make a diagnosis, for example, for lung nodules or skin lesions, they look for visual features such as the roundness, the margins, the texture, the intensity, and for example, the color if the doctor is a dermatologist. And then the doctors rate those visual attributes. So they say the lobulation is high, the shape is ovoid linear, it's not spherical, or it's not linear, but it's like a mix. The speculation is high or low. And then after they rated those attributes, there are predefined rules or diagnostic rules where it's very clear what attribute combinations lead to which diagnosis. So this is a reasoning process we adopted into our AI models. However, we had to quickly realize that there are very few data sets that not only come with a diagnosis label, but also of a label of those attributes. So we also need ground truth values for, is the speculation high or low? So this is why we came up with Funny Nodules, which is a framework for synthetic data generation. While I'm now showing you one setting of this framework, it can be customized to whatever data set you want. So in this case, we defined 6 attributes, for example, the roundness or speculation, and then we used very simple parameterized algorithms to develop those images. For example, for speculation, we implemented angular contour perturbation, or for edge sharpness, we used Gaussian blur. These attributes come then with labels between 1 and 5, except for the internal structure, which is binary, whether it's present or absent. We also then defined a targeted diagnosis label, and here we were inspired by the dermatologists who use a score-based rating, so they look at the ratings of the attributes, and then depending on whether they are reaching a threshold, this adds or lowers a diagnostic score, and then depending on the score, they give the target diagnosis label. We also added one more complex rule, which is a correlated attribute to target rule. So depending on whether an internal structure is present in the image, the roundness has a positive or a negative effect on that score. So again, these target rules are fully customizable depending on how you want to, or what you want to evaluate in your model. And let's come to the evaluation. Just as black box models, we can also evaluate attribute-based AI models on the prediction accuracy of the diagnosis score, as well as of the attribute score, because the attributes are also learned in a supervised manner. But what I'm more interested in is the relation between the attribute score and the diagnosis score. So is a model able to grasp those attribute to target rules? So this is where the framework is quite nice, because we can simulate endless examples, and also we can change one sample in regards of only one attribute, and then we can see whether the models also predict the same trend. So for example, for roundness, if this sample becomes less round, then the target increases. This is possible because the synthesis is again like a parameterized algorithm, so we can fix the seed, we can fix all the other attribute scores, but we can just change the roundness, and then we can make those sensitivity analysis. So we tested 5 models. 3 of them reflect this hierarchical prediction reasoning, so where they first predict the attributes and then the target. And we also used ResNet and DenseNet for comparison, and they do the attribute and target prediction in the last layer together. In black, you see the ground truth, and here for speculation, we can see that all models are able to reflect this trend. So when speculation increases, the target increases, and the model predictions also did that. We can do this for the other attributes as well. And now I want to also highlight this one correlated rule that I talked about earlier. So depending on whether an internal structure is absent or present, the roundness increases or decreases the target score. And these are the results, and this was very surprising for me, because none of the model reflected this trend without a bias, or even they had the opposite trend for where the internal structure is present, even though all models were really good able to predict whether an internal structure is there or not. However, they were not able to translate this into the correct rules. So this was very eye-opening for me, that none of the models were able to learn this rule, which is actually very simple, so every doctor could learn it in a split second during their studies, but the models were not able to do that. So there is some missing complexity in the model maybe. Another nice feature of this framework is that we can also generate attribute-specific region of interest masks. So what this means is that during the generation of the images with the parameterized algorithm, we can also mask the region where the attribute manifestates in the images automatically. So for example, for the speculation, during the image synthesis, we can already mask those little spikes, those little noses. If we now have a model that also outputs the attention heat maps of those attributes, we can now compare whether the model focused on the correct regions, but not on a class level, but on an attribute level, which can be very helpful in medicine, where the appearance of the same disease can vary a lot. So to do this on the attribute level can help sometimes. Other ideas to use this data set for evaluation is, for example, that we can, of course, vary the data set sizes, so we can create optimal scenarios where the data set sizes are very high. We can simulate sparse data, sparse annotation scenarios and compare it to the optimal scenario. We can also add background noise to evaluate whether a model is background independent, or if the model has problem to compare the background with the foreground. Then we can also compare the performance accuracy between diagnosis and attribute labels. So just imagine if the attribute performance is very good, so the model is able to predict all those attribute labels, but it's not able to do the diagnosis correctly, then this is an indication that there might be too little complexity between attribute and diagnosis layer. On the other hand side, if the diagnosis performance is very good, but the attribute performance is very low, this might be an indication that the model found some spurious correlations. Also, I just showed you model agnostic analysis methods, but you can also use it for more model-specific analysis where you look into the information process within the model. So let's sum up. This framework allows for in-depth analysis and also systematic analysis of attribute-based AI models, so to evaluate the attribute-to-target rules, but also other features. However, I want to also emphasize, of course, limitations. So I would be very careful to translate model performance on like the synthetic data sets directly to the real data set. So for example, if a model does a very good job in predicting the roundness on a funny nodules sample, it doesn't translate into the model doing a good job in the real data set. So we not only use real data set and synthetic data set, but also, of course, the human in the loop for explainable AI. Thank you.
The presentation is open for questions.
Hi, thank you for the great presentation. Yep. I have a basic question regarding the attributes. So how did you come up with these attributes, and did you left some out, or would you extend it by some additional attributes that you could expect improving your framework?
So we were inspired by the LIDC dataset, which uses a similar set of attributes, but not exactly the same one. And we just decided to use 6 attributes now, but we can also increase the number or decrease it. So we just used one set, but it's very easy in this framework, and you can also check the code to add or remove attributes. You just have to have one idea how you want to do it in a parameterized fashion so that you can set scores. I think the background independence is also very relevant for many tasks. So I think also the ratio of background noise and object could be interesting in the future to analyze.
May I ask a follow-up? Or so if you would advise to come up with a meta framework of deciding which kind of attributes for which kind of applications might be relevant, do you have ideas how to do that?
So for a specific medical task?
Yeah, exactly.
Here I would be careful to design attributes that are also happening in the real data set, just because you cannot translate the performances very well. I would more look at in a way that you can understand the complexity within the attribute to target rules. So whether it's like a threshold-based rules, because we all have this, like if I talk to doctors, they have those rules in mind. So I'd more look into like the complexity in this, that this mirrors the real data set.
Okay, thank you.
Thank you very much for your questions.
Thank you. Thank you for the talk. I had the same question, and then I was thinking, how did you manage to control the dependence between the different attributes? For example, like if you have higher than intensity and the size, they might have like some kind of correlation between the attributes. Did you have any experiments on that?
Yeah, so this is where I failed in the beginning. So this is a very good question. So for example, I first implemented all the other attributes, and then in the end, I did the scaling of the size, because otherwise the like roundness attribute could like mess up with my size attribute.
Yeah,
so
yeah.
you have to be very careful in which order you add which attribute feature. It's actually a very good point.
Okay, and this framework is totally designed for like dermatology data sets. So for example, for cell-based data set or this kind, you haven't tried this framework on that? Like the cell shapes or like the roundness of the cell?
So it was inspired by lung nodules, but and skin lesions.
Yeah.
But yeah, sure, you can also simulate cell data sets, but again, be careful with like translating the like accuracy or performance infos to real data sets. But like everything that is like an object and then it changes in visual features, like with like these features, yeah, you could try it out and just get insights for your model where it has weaknesses. And also, I think the data set size variations are quite helpful to compare different models. But yeah, for other medical tasks, other attributes and also other appearances might be more relevant.
Thank you.
Speak again.
Okay, so the second oral presentation is on future morph toward predicting future deformation fields in longitudinal imaging. However, because the speaker has left early, so we have a video to show this presentation.
I will present it as the second offer. We make sure so you can just take up the presentation instead. So do I. PowerPoint to yeah, the PowerPoint. Okay. I'm the second offer. I will also teach you for this. No, the future morph paper. So there should be the future morph. What is this? Okay, I can send you the presentation, and then first maybe to the next presentation when I go through it. Does that make sense?
我们收到之后，我们收到这个刚那个而已，就是没有它的投影片。对啊，因为之前收到的是这个。它的 number 是哪一个？它是这个。Is this copy yours?
Okay, so we will have this as an in-person presentation again. Yeah, maybe let's give a few more minutes to the speaker for these preparations.
I'm sorry. I thought this was communicated to you about is this one? Yes. Which one? It's 244. No, it's this one. Oh no, shit.
他拿错档案，他拿错档案，
他放错
档案。
It's PowerPoint.
you.
Oh, I think. Yeah, feel free to start when you're ready.
Hello, everyone. Thank you for your attention. My name is Roel. I am the second author. I'm substituting today for Sama Kawalet, who unfortunately could not be here today as she has her wedding to attend to, and with the impeding typhoon, she unfortunately couldn't make it today and she had to reschedule her flight. So today I will be presenting to you Future Morph towards predicting future deformation fields in longitudinal imaging. The basic concept behind Future Morph is that we want to predict how the brain basically deforms into the future. And since most of the deformations that take place in the brain are mostly due to geometric changes, while relatively little anatomy actually changes, it makes a lot of sense to not do it based on the voxel space, but rather to basically infer the underlying deformable geometric deformation. So, as opposed to typical image registration, in which we typically have access to a source and a target scan, we only have access to a scan at time point 0, and we basically want to see how the scan evolves over time, over the years. So here, for example, you can see that as the time evolves in years to the right, the brain deforms more and more. So, as I said, one of the important things here is that we want to predict the future scan. And this is basically based on geometrical changes. What we typically see in generative modeling is that we feed some sort of baseline scan and we just directly try to predict the future version of that brain image. But typically, it's much more constrained than that, and especially if we are only focused on certain underlying diseases like Alzheimer's, which are mostly focused on enlargement of the ventricles, changes in hippocampus volume. It makes much more sense to constrain our models to only predict the deformation vector fields. So that's why it also forms a new perspective for longitudinal imaging, where we can hopefully already quantify the volume loss and track things like Alzheimer's disease. So the way that we define these problems is that we basically have access during training to 2 input scans, where we have a scan acquired at time point 0 and another at time point 1, where time point 1 always takes place after the first time point. Both of those are 3D images, and we can define a delta t, which is the time interval between the acquisition of the first scan and the acquisition of the second scan. And then what we try to predict is the deformation vector field, which characterizes the geometrical scale changes. So we basically try to identify this field, phi, which we can apply to the input image, which then predicts how the output image looks at time point 1. So the way that we go about this is that, as I said, as opposed to regular image registration, where we have access to a source and a target volume, the only thing that we have access to in this case is only the source volume, next to some additional metadata. So we typically know the age of the patient, the sex of the patient, and obviously also the time difference between the first scan and the second acquisition scan. You can, from a registration perspective, see it as that this metadata replaces the second scan, and that based on that we try to predict a similar deformation vector field. This is also why, essentially, we can base the entire framework around a previously existing method called voxel morph, which typically takes a source and target image and, based on those, infers the underlying deformation vector field. Except now we only feed the input source image, and we condition the encoder-decoder structure on the underlying metadata, which we just described. Furthermore, then in order to make it diffeomorphic, we integrate the output of this deformation vector field over time. So we have a velocity vector field, we integrate it, and we get a deformation vector field. Then by applying this spatial transform, we get the predicted underlying image scan at time point 1. We propose to do this in 2 different ways. First of all, the most free conditional variant is where we apply feature-wise linear modulation. where we basically extract a vector from the metadata, and we use that to condition every of the encoder-decoder layers in order to scale and bias the outputs of those layers. Second of all, we apply another variant in which we don't include the delta t metadata directly in the metadata variable itself, but we only apply the delta t condition during integration. So we use scaling and squaring only in the integration phase. So the actual encoder-decoder instruction has no access to the delta t information. As some results, FutureMorph predicts realistic future MRI images. What you can see based on these two examples on the top and on the bottom is that the target and predicted volumes, especially for these ventricles that are highlighted here in the middle, which are some of the most obvious geometric changes that we can typically observe in the brain, match quite nicely between the predicted and target image. And if we then look to the quantified deformation vector fields, when we compare it to a voxel morph baseline, which is sort of our upper bound in how well we can predict the future image, we can see that the deformation vector fields are quite nicely aligned. Similarly for the warping fields. Furthermore, since we can now apply this on the dataset-based level, and we can vary the delta t that we condition the patient on, we can also identify these trends in how these patient deformation vectors and deformation vector fields evolve over time. What's especially interesting to see here is that if we compare FutureMorph to the FutureMorph variant, which only applies delta t scaling in the integration, we can see that the regular FutureMorph variant allows us to more naturally express sort of the exponentially change of volume in the brain. Well, because if we don't actually give the encoder-decoder access to this metadata during in the actual unit itself, it is sort of forced to linearly extrapolate. Furthermore, we can also capture growth trends between conditional or regular control patients, which are depicted in the top, and Alzheimer patients in the bottom. And as we can see, as the person ages, we can see that it predicts this change in growth quite nicely. And similarly, if we try to do the same for hippocampus changes, we can see that this volume typically decreases over time, and this trend is also captured quite nicely. We evaluate on a number of voxel-based metrics and in terms of some segmentation-based metrics, where typically the results are quite similar between FutureMorph and FutureMorph-S. And they reach the upper bound quite closely, which is voxel morph. But this is why we also decided to do an additional evaluation to further identify the difference between FutureMorph and FutureMorph-S, where once again, if we do these predictions for varying delta t's, we can see that this exponential decay is modeled much more clearly in the regular FutureMorph variant compared to FutureMorph-S. So in summary, FutureMorph predicts the future follow-up images just by defining the geometrical changes over time. And this is achieved by conditioning the underlying architectural metadata. And in this way, we can condition it on patient-specific priors rather than average priors. Thank you for your attention.
This is open for Q&As, questions. Any questions? Maybe I will have one while waiting for questions from the audience. So you are considering these geometric changes of that. But as we know, as it aging, there might also be appearance of some tissue changes, right? Like appearance of lesions, white matter hyperintensities. How do you think you could model that as well?
That's absolutely true. This model specifically focuses on diseases which are coupled to geometric changes of the brain. Indeed, if we, for example, have a tumor appearing over time which was not present at time point 0, then this method will obviously not be able to take that into account. But for something like Alzheimer's disease, it's a perfect match.
Questions there.
Hi, thank you for your talk. So I have a question. So when you're training, so the interval between different time points are usually fixed, like 6 months or 12 months. Like, how do you manage this discrete time points? But when you inference, you have a continuous timeline.
I can only give like half an answer since I did not actually do the implementation myself. But as I think it is, we have quite a lot of variation between the delta t's and the actual training data, which then allows us to at test time infer basically at any delta t just by changing out the metadata.
Thank you.
Okay, yeah, let's thank the speakers again.
So we were told that the third speaker is not here, so we move to the next one.
Okay, so the next presentation will be on benchmarking the reproducibility of brain tissue segmentation across MRI scanners. So let's welcome the speaker.
Hi everyone. Yeah. Seems to be the last presentation before typhoon. So we'll have a little bit of entertainment here, I hope. So thank you for having me here. My name is Kate. I'm supported by Maastricht University, but currently I'm based in United Emirates and spent last year doing startup in dementia early screening in SS. So today we will be discussing benchmarking brain segmentation and why it's still relevant in 2026, although the topic itself is very old. And we will see it from the lenses of dementia, just because I think it's very illustrative and also it makes more sense now than we can really treat Alzheimer's. And now it's a very big market with a lot of opportunity for diagnostics, patient acquisition, outreach, and etc. So this is my brain. And we will try to find dementia in me. Should be very easy. So what we have female subject, 30-ish years, 3 repetitive scans on different scanners. How I get them? First, because I'm volunteering in my colleagues' fMRI projects, and then I'm asking them to send my data to me. So tips and tricks to how to get your brain MRI from your university. And second, I'm traveling to ex-USSR countries, then you can pay cash and basically do brain MRI for $100, so it's a second tip. I expect that if I have dementia, my amygdalas, okay, it's a speculation, but my amygdalas will be shrinking. So how do I measure if my amygdala volume stays the same? And it's a hard topic because amygdala is very small, and I have 3 different scanners. So I expect them to shrink if I have dementia. That's what I see. I see that the dyes is quite stable. I see a little bit of artifact of volume segmentation, but most importantly, I see that my 2 amygdalas are changing asymmetrically, and I kind of confused what's happening with my amygdalas. It shouldn't be explained by the biology of my brain. So to give you more concrete example, what is the scale of these changes? Here is blueberry, okay? Black dot is what volume will be eaten from my amygdala with Alzheimer. And orange dot is the change that I saw on my amygdalas within 6 years. Doesn't make much sense. But happily, I have a PhD in computer vision, so I can not only do this on one subject and cherry pick the example for the presentation, but I can also do a proper benchmarking. So how I decided to tackle the benchmarking of subcortical multi-domain segmentation. The study was actually inspired not by the task itself, but by two amazing data sets that I discovered, and I put them in the to-do folder in my PhD, and I actually returned back to these two data sets a couple years after. Then the Claude was able to do most of the routine for me. So first data set is Simon. It's a Canadian researcher who was scanning himself 100 times during 17 years. Okay? One subject, 100 head MRI scans in time. Open source. Second, traveling subjects from Japan. 9 people traveling every day across Japan to the new 3 Tesla scan. Again, open source. Amazing data sets. I will encourage you several times to look at them, because they are not included in most of foundational models we now have. Looking at the Japanese dataset of traveling subjects. All scans in this dataset are 3 Tesla, high quality, new MRIs. Visually, you see a little bit of contrast difference, but images are fine. Still, dyes between gray matter and white matter is not very consistent, but it doesn't. I don't yet know how to interpret that, and also I want to look at the subcortical areas. Let's set expectations. 9 people traveling each day in new scan. I expect to see 0 to 0 point something difference in their amygdalas, because these are good scans, and they are scanning every next day. But my expectations could be also derived by the market, by industry. So if you are following brain MRI and brain analysis market, you might have noticed icometrics acquisition and a lot of need for area measurement. Area is a hemorrhage or edema which is caused by amyloid accumulation in your brain. So these devices are FDA registered, and these are the reported accuracy that they expect to have on the same individual with the same scan settings. So these are expectations from accuracy of the models performed on the same scan. And given that the expectations are set, we are now looking at hippocampus and amygdalas on 9 sites and 15 subjects from traveling dataset. We expect to see still line. And these datasets also are amazing because they first 5 days, they are coming to the same scan for test-retest. So on the first 5 dots, you see that test-retest on the same scan is almost perfectly same, repetitive. But then you can see that even on the good, highly contrasted new scans, the changes in segmentation and volume estimations are dramatic. We expect to see from 0 to 2% volume difference That is what we see. And also there is a blueberry to give you an understanding that it is still very, very small morphological structures. Second is my second favorite, that said Simon. Individual scanning himself 100 times across 17 years. I hope I will be able to do so with myself and also to upload it. We expect to see his brain shrinking. That is what happened with our brains. So this dashed line is what we see, what we expect to see, the slope. Okay, it's speculative, but it should be in the signal. And here is what we can see on Free Surfer and Fast Surfer. They are both state-of-the-art methods for longitudinal assessment of the same person in time. So most of your Alzheimer scoring alignment will also start with similar alignment and assessment. So expectations are not met. And another important result of this work is that it's clearly seen that the boundary shapes and distances that we are used to apply for Bratz-like segmentations, they are not really reflective for clinically meaningful volumetric estimations. For example, here I compare volume consistency to dice score, and dice score is high and volume consistency is very low. Expectations are not met. In the case of small subcortical, very important regions, we are still far from being able to solve segmentation in a domain shift setting. A lot of questions are still there. And to answer my question, do I have dementia in my data? I need to understand what is the domain shift signal, what is my daily fluctuations in my typical brain, like hydration or etc., and what is my healthy aging signal, what is my pathology signal if it's there. 3 things that I want you to take home is that there is plenty of room for analysis. More small data sets are still not ever considered for blind test, so I encourage you to do this. What I see could be an interesting extension of this research is to try to apply domain adaptation from CAS-space, and also to do test set augmentation, to maybe get inspired by research done with avatars, with meta-like 3D perception groups who are doing different Gaussian splatting models, which we typically don't do here. And I encourage you to collaborate with me. Apart from MRI, there is still a big demand to recognize dementia before patient has MRI. How it could be done? With digital biomarkers, so variables. I personally looking at face features, which is also underexplored and present on MRI still. Fundus, and also I want to mention auto-research works that are also underrepresented here, but I think we could standardize all the segmentation pipelines and do more rigorous benchmarking. So I want to mention 2 brilliant posters downstairs from South Korea universities. The upper one is showing how to assess if person is smoking by the melanin content on the lip, maybe you saw it. And the second one is predicting sex and age on fundus. And this could be done at a scale before patient gets MRI. So this is me. Thank you. And I guess now we're ready for Typhoon.
Okay, the presentation is open for questions. So maybe I will have a first question to see if others' questions will come up. So the work mainly focuses on this brain tissue segmentation across MRIs. I'm wondering if there is any specific challenges with this reproducibility of this application, or is this more of a general issue of other applications as well?
I will try to rephrase the question to check that I understand you correctly. So, is the tissue segmentation reproducibility on brain MRI is a main problem, or if there are other problems in the domain adaptation field?
Well, similar, yeah. I think I think that's one part. And also I'm thinking like, is there any particular challenges with this reproducibility of this brain tissue segmentation?
I see. So my answer will be maybe strange, but I think there are no problems in industry, and industry is still functionable because there are FDA-cleared devices that they require repeating this assessment on the same scan, and it's typically not a problem. It becomes a problem only then you want to predict longitudinal data with unseen before domain, which is for now not a problem. For now, I think the industry problem is to find more people with a risk of Alzheimer and to predict them and to get them to neurologists. So generally, I don't think that it is a bottleneck. If it was a bottleneck, it would be solved already. Second question, if segmentation is the only problem. No, I believe there is still a big room for foundational models for brain MRIs with data harmonization, like measurement of the different lesions, abnormalities, and also room of just observational studies is pretty open. We still don't really know how brain is aging. We know that the gray matter should be shrinking, but we're not sure how in the white matter difference, how white matter will behave, what triggers what. Still a lot of problem with adolescent, how brains are forming. So yeah, brain MRIs, I think, in brain longevity is underexplored to some sense.
Okay, thank you. So maybe I had just one quick question. So you also talk about metrics, which indicates that probably neither of them will be the best ones. So do you have any thoughts on what could the metric should give us?
What again?
So what the desired metric could be for evaluating or benchmarking the reproducibility?
Yes. I'm not sure. I'm pretty sure that it is not DICE, that is not Hausdorff 95, this is not just volume. I'm pretty sure that we will be struggling with understanding where is the gray matter, still gray matter, and when it's already white matter, so the boundaries will be a hard problem for us, I believe. But there are metrics, as I was saying, that are used in Gaussian splatting in 3D perception that we never tried in our setting, in how to assess the uncertainty in boundaries, or at least I haven't seen them being used quantitatively. So this could be an aspiration, but I don't have a question here.
Okay, thank you. Thank you very much. Let's thank the speaker.
Okay. Our first spotlight presentation is on the stability and robustness of vision transformers for neurodegenerative disease classification by Anoy Levitt.
A single run of a medical AI model can look convincing and still be misleading. In this work, we study vision transformer for neurodegenerative disease classification and ask a simple question: is the reported performance stable? The clinical task is 5-class differential diagnosis from structural T1 weighted MRI. We classify controls, Alzheimer's disease, and 3 frontotemporal dementia variants: BV-FTD, NFV-PPA, and SV-PPA. This is a difficult settings because the rare FTD subtypes are underrepresented and phenotypes can overlap, and evaluation is affected by cohort shift across datasets. So the question is not only whether the model performs well, but whether its performance is reliable on this kind of clinical task. Here is the problem. We train the same vision transformer on the same MRI data with the same architecture. But when only the random seed changes, the model can converge to different decision boundaries. In a 5-class differential diagnosis task, this can mean different prediction for clinically relevant subtypes. So a single one may produce a strong number while still being highly dependent on initialization. This instability is amplified for vision transformer because they have weaker spatial inductive biases than CNNs. They can model long-range atrophy patterns, but on small, noisy, and imbalanced clinical cohorts, optimization becomes fragile. Instead of only changing the architecture, we stabilize the whole training and evaluation pipeline. During training, we combine balance sampling, 3D MRI augmentation, mix-up, lab smoothing, and exponential moving average of weights. At inference, we evaluate checkpoint ensembling, test time augmentation, and temperature scaling. The goal is simple: move from a model whose result depends strongly on the seed to a model whose performance is both higher and less variable. The effect is cumulative. On the out-of-domain evaluation, macro F1 increases from about 56 to 72, and Matthew correlation coefficient from about 64 to 71. But the important point is not only the performance gain. The instability interval also narrows, meaning that the result becomes less dependent or lucky or unlucky initialization. This is the central message of the paper. If the gain is smaller than the stochastic variability of the model, it is not reliable evidence. At the poster, I show which components really survive to this stability-aware evaluation. However, stabilization also reveals a trade-off. Better discrimination does not automatically mean better probabilities. When the model separates rare and overlapping phenotypes more aggressively, it can also become more overconfident. So calibration must be reported separately using metrics such as expected calibration error and Bayer score. A model can rank patient better while being less reliable in its confidence estimates. The take-home message is simple. Don't be fooled by single one performance. Check calibration, quantify uncertainty. For a medical imaging model, especially on small and imbalanced clinical cohorts, point estimates are not enough. Please come to the poster to see the full stability analysis and which reported gains are actually reliable. Thank you.
Okay, our second spotlight is on weight-space correlation analysis, quantifying feature utilization in deep learning models.
Hello, everybody. Today I'm going to talk about our work where we try to quantify the effect of shortcut learning. I hope by the end of this video, you will find some of this useful for your own work. Now, here we go. Suppose we start with a classification problem like this, where given an input image on the left, you try to predict the anatomy on the right. So you train this model into convergence, and then you achieve a UROC of 99.6. Now you're very satisfied with this. You take this model, you take it to your downstream applications. Now, later on, what you do is you open this model up a little bit, exposing the embeddings, and then you freeze the whole model. You attach an additional classification head to the embeddings, and this time you try to predict the scanner used in acquiring the image on the left. Now, to your surprise, if you train this model to convergence, you will get an AUROC of 91.4. Now, this comes as a surprise to you because this information should not be there in the embedding layer. But should you be worried? Yes and no. Because first of all, it should not supposed to be there, but still, just because the information is there, it doesn't mean your clinical classification prompt task has made use of that information, right? So how do we check whether this is being used in the clinical classification task? So this is what we propose. So if you take the weightage from your clinical classification head and compare it to the weightage from your scanner classification head, if they have very high cosine similarity, it means they are looking at the embeddings in a very similar way, and that's when you should get worried. If they're low, that means there's nothing to worry. But then you might argue that embeddings is living in a very high dimensional space, and that means they might be very sparse. Low similarity doesn't mean anything. But you're completely right. So our workaround on that is that if you take your whole training sets, compute the embeddings, and then compute the PCA matrix, you can then use this PCA matrix as a manifold projection that allows you to, in a sense, compress your weightage into a PCA space before you do your cosine similarity. Now, this, in a sense, is doing compression in a meaningful way because you are making use of a PCA of your training sets, right? So now I'm going through very quickly some of our experiments. So what we do is we take our full data sets, we take a balanced subset of it, and then we take a biased subset of it. With the bias, you are supposed to see some sort of pattern between the weightage. Now, as you can see here, if you train a model using the full data set, you don't see any correlation between the plane weightage and the scanner weightage. But if you look at the bias one on the bottom, you see a very clear pattern there. Now, we didn't stop here because this is just our toy example. What we do is that we evaluate these on top of a model that we developed for spontaneous preterm birth predictions. Now, if you are curious about how we perform in that, I'm looking forward to talking to you at my posters. With that, thank you very much for your attention, and I look forward to talking to you.
So our third spotlight presentation is Sudico 10, so-called depth-guided, anatomically consistent fetal cortical surface reconstruction by Irina Grigorescu.
Good afternoon, everyone. My name is Irina, and I'm excited to share a work that brings together surface reconstruction with anatomical consistency in fetal MRI. The developing cortex rapidly transforms from a relatively smooth structure into a highly folded one. To quantify this, we move beyond volumetric measures and towards surface-based representations of the inner white matter and outer pure boundaries, enabling vertex-level analysis of cortical geometry. Classical neonatal pipelines can produce high-quality surfaces for neonatal MRIs, but they fail to generalize to fetal imaging, where lower resolution leads to partial volume effects that blur fine cortical structures. Recent deep learning approaches tackle surface reconstruction by deforming an initial template mesh to fit the target anatomy. While effective, they remain dependent on the training data set and often struggle to generalize to new cohorts. However, there is a more fundamental limitation in these methods, because surface reconstruction is treated purely as a geometric deformation problem without explicit anatomical constraints. There is no guarantee of vertex-wise correspondence across subjects. To illustrate this, let's track a set of vertices from the initial template shown on the left. As the mesh deforms into two different fetal subjects, we follow these vertices along their deformation trajectories, and what we observe is that anatomical correspondence is lost during this process. Both the propagated so-called depth map and the tracked vertices fail to align with subject-specific anatomy as the vertices land on opposite banks of the central sulcus. This means that although the surfaces look plausible, they are not directly comparable at the vertex level. As a result, any analysis of cortical development or group-level comparison requires a separate post-hoc alignment step, typically using spherical registration methods such as multimodal surface matching. To address this limitation, we introduce so-called depth-guided COTAN. The key idea is to guide surface deformation with anatomical information rather than geometry alone. We achieve this with a novel SOCNet module that estimates so-called depth during training and provides anatomical guidance throughout the deformation process. Our proposed method not only produces anatomically plausible cortical surfaces across two fetal datasets, but crucially, it preserves vertex-wise anatomical correspondence across subjects. The same template vertices now consistently map to the same anatomical locations across different fetal brains, enabling direct vertex-level comparisons across subjects. If you would like to take a closer look at the architecture or see our full quantitative evaluation, please come find me this afternoon at poster number 315. Thank you, and I look forward to discussing our results with you at this session.
Okay, so our last spotlight presentation is CSVR, Combined Surface and Volume Registration for Neonatal Brain MRI.
CSVR, a learning-based framework for combined surface and volumetric registration of neonatal brain MRI. Nonlinear image registration, or the spatial alignment of imaging data, is a cornerstone of neuroimaging analysis, facilitating comparisons of brain structures across individuals and over time. While traditional intensity or segmentation-driven volumetric registration methods generally achieve good alignment of subcortical regions, they often fail to capture correspondences between highly convoluted and variable cortical shapes. Surface-based methods yield improved cortical alignment by regularizing mappings geodesically along the cortical sheet, but are limited in that they do not extend to subcortical structures. A unified registration framework would address these limitations and enable integrated analysis of both domains. However, achieving this is challenging since matching heterogeneous cortical shapes implies large volumetric distortions local to the cortex. Existing methods therefore often rely upon iterative finite element solvers with long runtimes, or focus on aligning subjects of similar morphology such as twins, and they're generally designed for adult data. To overcome these challenges, we introduced CSVR, a deep learning-based framework for combined surface-to-volume registration of neonatal MRI. In brief, our method first performs surface-based registration, then propagates resulting displacements into volumetric images, which are input into a subsequent volumetric registration step for subcortical refinement. The two networks are jointly optimized to ensure smooth and consistent deformations across both domains, and registrations take on average only 0.73 seconds. Two architectural choices are central to this framework. First, both registration networks employ discrete optimization, reframing image matching as a classification problem where each displacement is selected from a quantized set of candidates, making the models highly robust to local minima and able to model large deformations while maintaining anatomically plausible warps. Second, we minimize distortions by registering subjects within clusters of similar cortical morphology, following Guo et al., with a long-term goal of performing a hierarchical registration and template creation, a method which has been shown to preserve anatomical detail and yield sharper population average templates. It's worth noting, however, that the clustering is based on the subject having similar folding patterns in at least one lobe, meaning that subjects within the same cluster can still exhibit very different overall brain morphology, as illustrated here. So CSVR is by no means restricted to aligning highly similar subjects. We benchmark against standard volumetric methods, as well as ablations consisting of our surface network interpolated directly into the volume, and our volumetric network alone. We also compare against CVS, Free Surfer's combined registration tool, which is to our knowledge the most widely used combined method, and find that CSVR achieves improved dice overlap compared to all methods across all tissue types. CSVR also produces smooth, biologically plausible deformations across both surface and volumetric domains. This stands in contrast to CVS, which we found to exhibit a high rate of folding artifacts in this population, a likely consequence of the method having been designed for adult data. Finally, we find that CSVR demonstrate the greatest gains over baseline methods for the most morphologically challenging subject pairs, likely due to its reliance on discrete optimization. Please come and find me at the poster session between 1:30 and 4:15 for more details. Thank you.
That's the end of the session, and thank all of you. And we have the poster session downstairs.
Yeah, so basically, welcome to basically our last session, but one of basically most exciting session, like closing and also award ceremony. So actually, it's wonderful to see there's still like some people here. So like with us to become like this a conference to the close. And basically over the past few years, we already enjoy like outstanding scientific program and also like inspiring keynote talks and also like engaging like discussion and also many opportunities to connect with the friends and colleagues from around the world. And this makes this year, MIDL 2026, a truly memorable conference. And also before we begin, on behalf of our organizing committee, I would like to thank all of our authors, reviewers, keynote speakers, and also session chairs, sponsors, and also volunteers. So basically, every participants to make this year's MIDL a very successful conference. So thank you all. Yeah. And basically during this conference, so we have a pleasure of recognizing several outstanding contributions for the award. So basically this award celebrates not only the scientific scientific innovation and also like the distinctions to make our community to the forward. So basically to begin with, we would like to first with our basically the award part. And before we begin with the awarding part, I would like to still take a moment to thank all of the sponsors for their generous support. So basically these contributions and also the partnership play a very important role in making this conference and also this award possible. So thank you again. Okay, now let me briefly introduce basically this year award categories. So basically we have like 3 scientific paper awards. So the Best Oral Award, Best Poster Award, Best Spotlight Award. And basically like Best Oral Award and also Best Poster Award following the past year's experience, we will recognize like 1 winners and also 1 runner-up. So basically celebrate the some of the most outstanding papers present at the conference. And this year also marked the introductions of our new Spotlight presentation format. So we also recognized the 1 winners and also 1 runner-up for Best Spotlight Award. And also, you see that we will also recognize the Outstanding Reviewer Award. So basically to recognize the reviewers who have made the outstanding contributions to the review process. Okay, so basically let's begin with the Outstanding Reviewer Awards. So basically in selection, we took into account of both the numbers of the complete reviewers and also the overall quality of the review. And we gave the particular considerations to the reviewers which received the strong nominations of our area chair and also the generous accepted emergency review request. So let's see the results. This year's Outstanding Review Awards goes to this 22 reviewers. So congratulations, and if you are here, so please feel free to stand up. Is there anyone still here? Okay. So basically we will update all these names of our recipients into our website later. Okay, thank you. And then we will move on to this scientific paper awards. So basically the recipients were selected jointly by our session chair and also program chair based on the review results, the scientific contribution of the paper, also the quality of the presentation. So basically let's begin with the Best Poster Award. So first, the MIDL Best Poster Award runner-up goes to the paper titled Evaluation of 3D Ultrasound Reconstruction and 2D 3D Segmentation for Neonatal Hip Dysplasia Scanning. So is there any of the any of the author here? Oh, great. So please come to the front and we will give you the certificates and we can take a photo. Congratulations. You can go to the stage, on the stage. So basically, our session chair, Professor Lü, will give the certificates, and we can take a photo here. Yeah, let's give another block. Thank you, thank you. Congratulations again. Okay, so next is the Best Poster Award winner. So the MIDL 2026 Best Poster Award winner goes to the paper entitled Landmark, a self-configuring method for 3D medical landmark detection. Is any of the authors here? So you can come to the stage. Okay, great. Congratulations. Thank you. Congratulations again. Okay, next is our Spotlight Award. So the MIDL 2026 Best Spotlight Award runner-up goes to the paper Endo-SEMI-S towards robust semi-supervised image segmentation for endoscopy video. Congratulations. Okay, congratulations again. Okay, so next goes to the Spotlight Award winner part. So the MIDL 2026 Best Spotlight Award winner goes to the paper democratizing pathological palette and open pipeline and data set for host-less vision language model. Congratulations. Yeah, please. Congratulations. Okay, now let's go to the Best Oral Award. So the MIDL 2026 Best Oral Award runner-up goes to the paper at Dino, domain adversary self-supervised representation learning for spatial proteomics. So is there any author here? Okay, so basically we will send the emails to the authors and also like the soft copy of our certificates. Okay, great. So yeah, let's move on to like the most exciting one. One of the most exciting one is our Best Oral Award winner. So basically the MIDL 2026 Best Oral Award winner goes to the paper titled Fast and Explicit Slice to Volume Reconstruction with 3D Gaussian primitive with analytics point spread function modeling. Congratulations. Thank you. Okay, congratulations. Great. Okay, so basically, again, congratulations to all the recipients of the award. And also, still, like, thank everyone again who's contributes to make this year's MIDL like very successful and memorable. And also today, we are delighted to have the organizing committee of the IPME 2027 here with us today and want to share some words. So now let me hand over to Dr. Ismail Ben Aryat and also Dr. Apak Uhus for introducing IPME 2077. Okay.
All right, thank you very much. As the president of the IPME board, it is my great pleasure to introduce Dr. Ismail Ben Ayed, who is the program chair of the next IPME.
Hello, everybody. So we will be hosting IPME in a nice lakeshore area eastern of Montreal, Canada, in 2027, around the end of June. So perhaps for those of you who do not know IPME, information processing in medical imaging, it would be probably safe to say it's the oldest AI for medical imaging conferences. Well, back then in the 70s, maybe it was known as statistical learning rather than AI. So maybe I have a nice video to show you the area where, and the tradition of the conference is to be in kind of remote, nice natural area, kind of isolated, although it's just 1 hour drive for Montreal, so you guys could also come to Montreal. So I'll try to play the video. So the format of the conference also will allow endless discussions actually during the session and a lot of networking for junior people, in fact. And of course, you know, a lot of fun, as you could see, nature activity, but also at the end of the day, a lot of social activity. So on site, there is very nice also catering services. So we will make sure everything will go great. Perhaps we will not provide as much food as in this venue, but we will make sure to have a lot of drinks and beer at the end of the day after the exhausting sessions.
The board does not approve of this message. Drink responsibly.
Okay, so what can I say? That's it, I guess. Maybe the next one. So this is the area, and see you in Canada. In end of June 27, and the deadline is early December. Okay.
Thank you.
Yeah, so thanks again for introducing this great opportunity. And basically, we look very much to this conference, IPME 2027. Yeah, and next, let me welcome our General Chair, Dr. Lilas, to give some words, the closing words.
Okay, thanks for hanging out with us until now, and think that tomorrow and tonight, pay attention to your safety. But generally speaking, like Taiwan, Taipei is a very, very nice place, and probably, in my opinion, keeps the best Chinese culture, 5,000 years of Chinese culture. And I hope you all enjoy MIDL and enjoy Taipei, and have some time hang out and to see things and taste the different meals, and there are many different restaurants, and very affordable and very delicious. And for me, it's like this is actually the first time we bring MIDL. You know, MIDL used to be like 1 year in Europe, other year in America, right? And also MIDL is mostly like organized by German and people from Holland, right? And but I think I hope like we bring something new, and from the Asian cushion or Asian flavor or something like into this area, this medical imaging analysis and deep learning and the statistical learning going forward. I think this will conclude this middle 2026 version, and I hope you all have the safety flying back home, and before that, enjoy Taiwan. Thank you.
Thank you. So my name is Geert Litjens, and on behalf of the MIDL board and the MIDL Foundation, I'd like to say a few words, and I'll try to keep it short. I know you all want to get going. And then we'll end with announcing where MIDL 2027 will be. But first and foremost, I would like to ask you for a hand for our local organizers, our program committee of 2026, and all the amazing volunteers who have made these past 3 days very tasty, very smooth, and with excellent science. And then I would like to ask a second hand for all of you for sticking around, surviving or will be surviving through a typhoon, for the great discussions, the great networking, the amazing karaoke last night for the people who were there. And yeah, hand for yourself, please. Okay, there are two more things I would like to say. So I know that everybody will be sad that the physical conference is ending, but as a foundation, we also organize many events throughout the year, from winter workshops to reviewing workshops to pre-conference events. So please follow the website if you want to participate. Most of these are organized by our awesome Young Researcher Board. If you are interested in that, do reach out. We're always looking for more people, more help. Yeah, and with that, I think the second most important thing after the awards is where will MIDL be next year? And I would like to invite Wilson Silva to do the introduction for that.
Well, thank you very much, Geert. I would like to start by, again, thanking the organization of this year's MIDL. It was really nice to be in Taiwan, and it was an amazing event. And so now it's my responsibility to tell you where the next edition will be. So for all the foodie lovers here, don't worry, it will go to Europe, but it will go to Good Food Europe. And without further ado, the next edition will be in So as you could just see, next edition will be in Porto, Portugal. First time in Southern Europe. Place with amazing food and also like very beautiful sights to see. And I'm one of the organizers, but we are a big team that is working hard to make sure that next MIDL will be at least as good as this one. And this is the team behind, or at least the main team behind the organization of next year's MIDL. So I hope to see you all in Porto next year to drink some very nice port wine and eat pastel nata. Obrigado.
Enjoy your night and make sure have a good dinner before typhoon.